Okay, well, welcome back to day 4 of training. We are going to pick up where we left off, talking about some additional things that we're going to need for this modeling example. So yesterday we spent the last bit of time introducing the conveyor objects. And because conveyors are often used in conjunction with racks, I thought this would be a good time to introduce the racking objects as well. Now, similar to the conveyors, the rack objects are a pretty deep tool. They have a lot going on. And in this section, we're really just going to start to scratch the surface and also, like I said, introduce the basics of what we need to know about in order to use objects like racks. The big thing about the rack objects is to understand that they are basically a queue with three-dimensional storage options. So we have a rack is defined by a system of levels where you have vertical shelves, bays where we have horizontal shelves, and then individual storage slots that are within each individual cell defined by an individual bay and level location. So like, for example, in this picture, we're seeing a two-dimensional layout of a rack object. And this is part of the object properties, by the way. We'll take a look at this in a minute. Where if you were to look at, say, level 3 and bay 6, there are two individual storage slots within that individual cell. So kind of think of the levels and bays as rows and columns of like a table. And then within each cell of that table, you have a number of storage slots that you could put flow items into. So let's take a look at using a rack kind of in a simple way. I'll just use this little example that I started working with yesterday. And rather than having it sync here, I'm going to drag out a rack. Now, the rack by default is going to look like this. And similar to our other objects, you can drag it around and position it in space. If you right click on one of these cones, you can rotate the rack to change its orientation. One thing to note about the rack is that we try to kind of color coordinate some aspects of the rack so that some things work as like a visual cue. Like, for example, the face of the rack is marked by these orange shelves, and the back of the rack is marked by these gray shelves. So this would be like your picking and placing surface. When operators or task executors need to be able to put things into a rack, they will approach it on the orange side. And when they need to take things out of the rack, they'll also approach it from the orange side. Now, as far as modifying the dimensions of the rack, like on the slide, there is this two-dimensional view where you can input as a value the number of bays and levels. And that's found by clicking on the rack and going to the option that says edit dimensions. And it shows you this two-dimensional layout view of the individual levels, bays, and slots in the rack. For quick dimension changes, you can also use these colored cones on the rack itself. Like, for example, if you go to the blue cone, left click and hold and drag your mouse down, that will remove levels from the rack. If you left click and hold on the red cone and move your mouse, that will remove bays from the rack. And if you left click and hold on the green cone, that will add depth to the shelves. Okay, and notice that that updated the dimensions table that we have over here as well. So in addition to being able to adjust the number of bays or levels on a rack, you can also adjust the number of slots. You can't do that within the 3D environment like with the cones, but on the dimensions table, if you highlight an individual cell, you could say that there are maybe 3 slots in this particular bay. And so it would know that we've got 2 slots here, 3 slots when we get here, and then 2 slots again when we move on over to the next bay. And if you want to do that for, set the number of slots for the entire rack, then all you'd have to do is click off so that like the entire dimensions table is clear. And then when it says slots per bay, you could just like type the number 1 or something, and it would know, okay, now, like as a global setting, all of the slots, or rather all of the bays in the rack are set to a single storage slot. Now, the reason why we have individual storage slots on this is mostly so that you can fine tune the way that flow items are placed into the rack. So just to kind of give us a little bit of differentiation, I'm going to say that the first bay, first level has one slot, and at the second bay, or rather the second level of the first bay, is going to have 3 slots, and we'll just see what that looks like. So if I want to be able to send flow items to this rack, I just have to make a port connection from an object to the rack. And that can be any object too, right? We're using a conveyor here, but you know, if you want to send things into a rack from like a processor or anything else, it's all the same. So if we run this model just for a second and we get flow items that are going to come down the conveyor and get put into the rack, notice that by default, the placement algorithm that we use is to start in the first level of the first bay and the first slot. And we will fill that first slot all the way until it's full in terms of the 3-dimensional space before moving on to the next level of the first bay and then the first slot of that bay. So we're going to fill this first level, first bay, first slot area here on the ground. And because I made the shelves pretty deep, that's gonna take a while. So we'll just speed it up for a minute. And so here you can start to see that the number of flow items is like right up to the top of the shelf. There's no more room for another flow item. And so the next flow item that comes to the rack says, okay, that slot is full now. So now I'll move up to the next level of that bay. And now we're filling the first slot. But now there are 3 slots in this bay. So it's going to look a little bit different when those flow items arrive, where it tries to fill the slots as best as it can. So because I said there are 3 slots, and those slots have a width parameter, notice that if you highlight those slots in the dimensions table, you can see that the slot width is set to 0.83 meters. These flow items have a width of, I believe, 0.6 meters. So that's why there is empty space, right? Because the width of the flow item is not exactly the width of the slot. And so that's creating like a little bit of buffer space in between. But using the dimensions table, you can also adjust any of these values if you want to change what the slot width should be, level height, bay width, any of that. You can adjust how flow items occupy space in these shelves. There's also a set of options that you can get to using this button that's called slot padding. Slot padding would allow you to say that there is a certain amount of buffer space that is just assumed into the shelves. So you could say that, like here, we're getting kind of like wall to wall stacking of flow items. But like if I click on this shelf and said that we had left padding of like 0.3 meters and we had right padding of 0.3 meters, you can kind of see that in the layout table, just to make it bigger, it's easier to see that there's like some grayed out space on the sides. And let's also add like some top padding. Let's add like a 0.3 top padding. And so now the actual storable area in that shelf is only what's shaded in blue. So hopefully that's coming across okay in the Zoom. It's a really light gray and a really light blue. But you can kind of see that there's this little border around the outside of the slot now that says that this area is not considered storable. So when you run the model, then the visual of it, and we'll just kind of speed through this a little bit and try and get more flow items stacked up. There we go. So when we get to this point, like notice that the first slot has no adjustments. So it fills the area pretty much wall to wall where we have 3 slots, we have a little bit of buffer space between them just because the width of the flow items versus the width of the slot. And then when we get up to this 3rd level, see the buffer area that is the slot padding that goes around that section of the slot. So we try to give you a lot of controls about how things are stored in the rack, not only by giving you this the visual of having shelves and everything like that, but also being able to control like different ways that you might essentially assign space to the flow items, where they have a certain amount of space that they're allowed to occupy. Okay, any questions there at all so far? So just notice as we let this run that the flow items, again, the progression that they use to fill up the rack is they start with the first bay, first level, first slot, and then they move to the 2nd level, first bay, first slot, and then the 2nd slot, and then the 3rd slot, and then the 3rd level, first bay, first slot, so on and so on and so on, until it eventually, like, because there are no outputs from this rack right now, eventually we're going to get to a point where the rack is full if we just keep sending flow items to it. So that's the default way that flow items are placed into the rack. And this is actually controlled by a property on the rack that is called the slot assignment strategy. So if we look in the rack properties, oh shoot, I accidentally changed the visuals here. Got to be careful with that scroll wheel sometimes. So this is being handled by the slot assignment strategy. And notice that the slot assignment strategy says that we are going to fill the first slot with available space. And if you want to see a little bit more, granted, it's not much more, but if you click on the edit button associated with that, it says that this condition is always true. We're always going to use this method, and the slot has to have space. So with this checked, the dimensions of the slot will be compared against the dimensions of the flow item, and that will be used as kind of the way that things are placed into those slots, right? So like if I were to come to my flow items and say, well, actually, you're not those default sizes, I could go to the toolbox and say that in what's called the flow item bin, the flow item bin is a place where all of the flow items that you could create are stored so you can access their properties before the model runs. It's like if we were to go to the box is defined as something that's 0.61 meters by 0.61 meters by 0.3 meters. But if I were to say that it is actually like a 1 by 1 by 0.5 box, right? It's a much larger flow item now. And that's going to have an impact on how flow items are stacked in this rack. Right? Now, kind of interesting about this is notice that this slot didn't get any flow items, right? Because this slot says that it has, or rather that shelf says that it has 3 slots, and those slots are only 0.83 meters wide. These boxes are already 1 meter wide. So they can't go into that shelf because they're too big for those storage slots. So when your slot assignment strategy involves this checking for available space part, which seems to be the default, most people don't ever turn that off in my experience, then that means that the size of the flow item will impact what slots are considered storable when flow items are sent to the rack. Okay, now there are other options for how you want to assign flow items to an available slot in the rack. If you go to the drop-down menu, there are some other ways that you could define this. But really, kind of what we expect people to do, and this is going a little bit beyond what we're going to demonstrate at this stage. What we expect people to do is to define some sort of a custom strategy for storing products in a rack, like especially if you're building a model that has to do with like warehousing. You'll probably set up something a little bit more complex, like an addressing scheme, where there are multiple racks that need to work together. and there is some sort of an addressing scheme that you set up where each individual slot is assigned an address, and those flow items will be assigned to a particular address within the racking system. So it's not, I mean, like, you can use the rack as a singular object like we're doing here, but there's also some cool advanced features that would allow you to use the rack as a single member of a larger system of storage, where you have to coordinate the placement of things in multiple racks. And maybe there are different cells of the rack that are assigned to different products that have these different addressing schemes working with them. But like I said, that kind of like a larger system-wide set of behaviors, a little bit beyond what we're going to talk about here. But I do want to show you a handy slot assignment strategy that kind of starts to head in that direction. And that's this one that I have highlighted right here that's called matching labels, where we can use the labels of the flow item to dictate what individual slots in the rack those flow items might be assigned to. So let me show you how to set something like this up. And so first of all, we're going to go to my source object, and we're going to assign some labels to these flow items. So let's do just something kind of simple where I'll go to the onCreation trigger of the source. So the onCreation trigger happens as a response to the creation of a flow item, like the name might suggest. And here we're going to say that we are going to set a label and a color, because I like setting colors on things, so it makes it easier to visually verify. And let's just say that we use the default value here, where it says the value of type is going to be a random number between 1 and 3. So really simple, just integer values 1, 2, 3. So just to see what that looks like, if you hit reset and run, you're going to see all these different color boxes that are flowing around. So we have red, green, and blue. And actually, let me fix this rack so that we can actually get things into this slot. So I'm going to say that there's only one slot here, just like the rest of the rack, just so that I can actually put flow items in that second level. Okay. So now that I have labels on my flow items, maybe I want to say that certain flow items with certain label values for type need to be placed in particular locations in the rack. So we have labels on the flow item already, but one thing that's kind of cool about the warehouse library where the rack object comes from is there is a tool that says that we can paint slot labels. So this means that we can actually assign labels to individual slots in the rack. So like we can have labels on just about anything, right? Like we talked about, including slots in a rack. So if you choose this option, if you just click on it in the library, it turns your cursor into this paintbrush. And then at the top of the properties panel, you have this option to set a label name and a label value, which will automatically set a color to the slots, at least while you're in the label painting mode. So like, for example, if we say that there is a label called, I'll call this slot type, that means that the label that I assign to the slots will be named slot type. And then if I say that I want it to have a value of 1, then when I come out here to the rack, I can actually click and drag and paint individual slots in the rack with that label value. So now these red slots are all assigned a label named slot type, and the value of that label is a 1. Now, if I say that the value is a 2, I can maybe say that we have these slots set for type 2, and we'll say that these slots are set to slot type 3. Okay, now, so far all I've done is I've assigned labels to the slots, just like I assigned labels to the flow items. So if I come back to my rack and find that slot assignment strategy again, I can go to the drop-down menu and say that I want to assign slots by matching labels. And so this has a little expression in it that says that the label that's assigned to the slot has to be the same as the label value assigned to the item in order for the item to be assigned to that slot. So it has a couple of default label names in there that we would expect you to change. Like in my case, the label that I actually assigned to the assigned to the slot is called slot type, and the label that I assigned to the item is actually called type. And so if this expression is true, if the value of slot type is the same as the value of item type, then flow items will be assigned to that slot. So when you run the model then with that setup, then we'll see that the flow items are assigned to the slots that match their label values. And if you want to see the label values represented as the colors again, if you go back to the warehousing section of the library and click on that paint slot, where you get the paintbrush again, and it will show you the labels that are assigned to the slots, their values, and their colors. And notice that the progression again is the same, where it starts at the first level, first bay, and then the first slot that's assigned to that type of flow item. Okay, any questions there at all so far? Now, right now, with the way this little example is set up, flow items are never leaving the rack because I don't have any output ports. And again, one of the things that is a little bit outside the scope of what we're going to be able to talk about this week is that this is a fairly common thing with the way the racks are used, where they may have input ports, but they may not have output ports, because a lot of times when we're using the rack objects, it's because we're doing some kind of like an order picking type of a model. And we need to create custom task sequences essentially that tell pickers to go and retrieve items out of the rack according to some kind of a criteria. Like maybe you have an order that says I need XYZ SKUs, and now we're going to go find them in the rack and we're going to pull them out of the rack using a picker. That's like I said, it's a little bit more complex than we want to get into now, and we haven't really talked about some of the supporting features that we need to know about in order to understand how that kind of picking operation might work. So in lieu of that, if we want to treat the rack as just like a standard object, we can just give it output ports and allow flow items to leave according to their natural progression of events. Like for example, if I have like just another conveyor object here, and we'll send this to a sink. If I send flow items to the rack right now, the rack will behave a lot like a queue, in the sense that if there is someplace downstream where we want, I forgot to make the connection. Oops. Let's try that again. All right. So like I said, if we send things to the rack right now with an output port, it'll behave a lot like a queue, where it will only keep things in the rack as long as there is no downstream availability, right? So that's one of the reasons why having a rack without output ports is fairly common, because the removal of things from the rack is going to be controlled by some other kind of like a picking system. But in using the rack like any other standard object, like a queue or a processor, we can give it output ports, and the rack will know how to use those output ports and send things along. Now, the downside to this is that if we want to mimic like time that has to be spent in the rack to represent like delays associated with picking, we would have to make that something that the rack knows how to do. And we did. So if you go to the rack object and scroll through the properties, there is an option under the flow area that is called the minimum dwell time. Now, the job of the minimum dwell time is essentially to put a delay on flow items such that they will spend some amount of time in the rack before finally being released to the output ports. So the minimum dwell time is often used as an abstraction to allow flow items to spend some amount of time based on either distribution or maybe a table value in order to abstract the time necessary to spend in the rack before something gets picked. So it's not meant to be a replacement for a picking system if that's something that your model needs to study and needs to have a lot of detail about. But it is something that you can use just to say that, well, we know that flow items generally spend this amount of time in the rack, and so we will just give them a dwell time so that they stay in the rack for a while before they finally get released. Because right now, everything's just passing straight on through. But if we were to come back to the rack and say, okay, the minimum dwell time is going to be a set using a distribution, like maybe we're going to say that the minimum amount of time that they spend in the rack is like 60 seconds. The maximum amount of time they spend is 120 seconds. And usually they spend 100 seconds in the rack. You could take something like that, and the flow items will actually be placed into their appropriate slot like we expect them to be. And each flow item is now running a clock until their dwell time expires. And so because it's random, some flow items will spend more time in the rack than others. And then finally, they will be released using standard object logic to an output port, and then they'll just be sent downstream from that. Okay, and just for the sake of definition, the reason why it's called the minimum dwell time is because the total time in the rack is generally described as the minimum dwell time plus any time spent waiting for downstream availability. So by saying that you're setting the minimum dwell time, you're saying you have to spend at least this long in the rack, and then any additional waiting time if the downstream object from the rack is still busy. So you count this time first, and then you evaluate the downstream. And if the downstream object is available, then it gets sent. Otherwise, it might accrue additional waiting time as the downstream object is busy. So like if you were to send something from the rack to a processor or something like that, then you might have to accrue additional time spent in the rack as you wait for that downstream resource. Okay, any questions there at all? Cool. So exercise time. So we've got a model here that is going to incorporate aspects of using the conveyor system like we talked about yesterday, and also introducing the use of a racking object. And on this slide, you'll see the general layout of what we want things to look like. And the behavior that we're looking for is that the source is going to create flow items every 6.5 seconds on average using the exponential distribution. And when those flow items are created, we want to assign them a type label. We want to give them a label value that ranges from 1 to 4 using the D uniform distribution. And then we want those flow items to come onto this straight conveyor. And then we'll use this first decision point as a way to decide where flow items will be sent. So if their type is 1, we want to send them to this first lane. If type 2, we want to go to the second lane, and then type 3, and then also type 4. Notice here we have an operator who is going to be responsible for picking up flow items off of these lanes and placing them into our little rack. And initially, we want to place things into the rack using the default slot assignment strategy that says that we'll place things into the first available slot with space. Just in order to keep flow items in the rack for a little while, we will use a minimum dwell time using the normal distribution with a mean of 30 and a standard deviation of 5. And then we have 2 exit lanes of conveyors where we want the rack to alternate use of those lanes. So like the first flow item will use lane 1, second flow item lane 2, third flow item lane 1. And we can accomplish that by using the round robin rule found under the send to port option of the rack. And then we want to create a restricted area using these 3 decision points so that when flow items arrive to either of these 2 decision points, they will request access to a restricted area controlled by the downstream decision point. And so these two decision points will be the entrance to the restricted area, and this downstream one will be the exit from the restricted area. Once they clear the restricted area, they can continue down and go to a station object where there will be a 3-second process before they're finally released out to the sink. Okay, and then there's a couple of challenge sections, a couple of enhancements that you may want to explore, like trying to route the items out of the rack so that types 1 and 2 always use the same lane, lane 1, and types 3 and 4 always use the same lane, in this case, lane 2. So in the visual of the model, you would see the red and the green boxes always using the first lane, and the blue and the yellow boxes always using the second lane. And then also set up the model to see if you can place things into the rack such that all the same type of flow items are stored in the same slot. So like if you take this example, where we have slots 1, 2, 3, and 4, all the type 1 boxes would always be stored in these slots, all the type 2 boxes in these slots, type 3, and also type 4. So that when things come off the conveyor, they just have to go straight ahead into the rack, thereby reducing the travel time for our poor operator. Okay, does that sound good? Anyone have any questions on the description?
Regan, the description is great. Just out of curiosity, can you turn off the shadow effect on the grid?
Yeah, actually you can. In the model, there are a set of graphics options. If you go up to File and say Global Preferences, then under the Graphics tab, there is a checkbox where you can turn off shadows, or you can adjust the shadows if you want to leave the shadows on, but maybe like make them not quite so hard.
Thanks.
Or yeah, just turn them off altogether, like that. It's funny, the shadows were added probably about like 5 years ago or something like that. And I've actually been with FlexSim for like almost 15 years. And so when the shadows were first added in, it was like really disorienting, because I was like, oh my gosh, I'm not used to seeing all these shadows everywhere. But now I'm kind of oblivious to it. I forget that they're even there.
Nice. Creature of habit. Thanks.
No problem. Okay, so take a few minutes to give that a try. If you have questions along the way, let me know. This will probably take you around 20 to 30 minutes, thereabouts. And then I'll just check in with you guys in a few minutes, see how things are going, and then we'll plan on doing the walkthrough once you've all had a chance to give it a try. Okay, so let's just jump into the walkthrough really quick. So just to save a little bit of time, I already just constructed the objects. Hopefully that wasn't the stumbling block for anyone. But there are a couple of things to note, as Devin brought up, where you do need to watch out for the directions of the conveyors. Using the join conveyor tool is super convenient, but you do have to remember that when you make like these curved conveyors using the join conveyor tool, that you make sure you click on what you want to treat as the sending conveyor before clicking on the receiving conveyor. So you make sure like those curved sections are all pointed in the right direction. So it's a lot like port connections, where the direction and the order that you do things matters, right? To make sure that we go from sending to receiving, whether we're talking about a port connection for a sending receiving object, or the join conveyor tool where we're talking about a sending and receiving conveyor. Otherwise, I just set everything up the way that you would expect. I haven't done any of the logic yet. I've got my decision points, and I'm using decision points here as targets for where I want to send my flow items. So as I mentioned yesterday in the lead up to this stuff, you can use any object that is part of the conveyor system that you want as the target. I could have chosen the exit transfers as the target for my send item. I could have used a photo eye. I could have used the decision points.
How did you make those pickup points long again?
That's by first moving the the transfers off to the side, and then using the red triangles to expand them. And that's what allows for the predictive pickup that the operator can do, where he can try to intercept the flow item while it's traveling on the conveyor. Okay, and then just got my rack, my other conveyors, and I've already got these decision points down here that are set up for my restricted area. So let's just start right at the very beginning. And the first thing that we'll do is edit source, where we will say that the arrival rate, first of all, is every 6.5 seconds according to the exponential distribution. And then our triggers say on creation, set label and color, and then just change the D-uniform distribution to be 1 to 4. And if you wanted to change the label here, the label name of type, could if you wanted. If you wanted to call it something else, that's fine. But I'm just keeping it with the default just because it's simple. So that'll send my flow items onto this conveyor. And then right away, I want them to decide where they're going to go by hitting this decision point. So the option that I would choose to do this would be to say on arrival, and then send item by case, where I can take advantage of the fact that the default case function references my type label, which again is one of the reasons why you might keep the default label name on the source, because this way you don't have to remember what it is. You come over here to change it. So now I'm just going to add my 4 different destinations, and notice that the destinations are automatically referencing out objects from 1 to 4. So that would mean that my first out object for type 1 is this first decision point, my second out object, third out object, and fourth out object. So we just kind of see what we've got so far. We should just see that the flow items are just getting routed to their individual lanes. And because we haven't set anything else up yet, like the operator is not going to pick them up, we don't have the dwell time on the rack yet. So we're just kind of sending things, and we're just kind of testing to make sure that this part of what we're looking at works. And so far, it's looking pretty good. It looks like all of my flow items are going to the correct lane. So sorry, is there a question?
I did all of those things, and my closest lane does not want to. It's not running anything.
Okay, let's have a look at it. Oh, I think I've lost your audio too, Devin. I can see your screen, but if you're trying
Sorry,
to say
I
anything.
was on mute by accident.
Okay.
Yeah, so this one doesn't want to accept anything.
Yeah, and so the reason why is because it doesn't have a transfer from the curved conveyor to the straight conveyor. See how it doesn't have one of those little squares that joins the conveyors together? So it looks like you have one conveyor that is off the Z plane with another. So rotate your camera a little bit, and you'll probably notice that straight conveyor is taller than the curved conveyor.
Oh, yeah.
So just make sure they're on the right Z plane. And that's a really easy thing to mess up, because if you click on something and scroll, it'll just detach it from the object. So now it should be.
Yes. Thank you.
Yep, no problem. Okay, so now the next thing we need to do is get the operator involved. Now, one thing that can kind of take a lot of time with this kind of a model is that we have multiple objects that we need to set the properties for, and they're all basically doing the same thing, right? So you would click on this exit transfer and say that you want to use transport, and then you have to click on this one. But this is a good opportunity to show you guys a little shortcut. Another thing that we can do with the selected objects capability. So if we hold down the control key on the keyboard and do a single click on one of the transfers, you can see that it gets highlighted in red. I'm going to do that to all of these. And what's kind of cool is that if I have them all highlighted in red and click on one of them, if I come over to the properties panel and make a change, like saying that I want to use transport, it's going to tell me that 4 objects are changed, and it actually set the properties for all of the selected objects to be the same. So rather than having to go to each object individually and clicking use transport, I can just shift select them and then make that change once, and it will propagate that change out to all the selected objects. So that means now if I run the model, the operator will pick up from any of those lanes because we told them all to use transport. And so right now the operator is placing things into the rack using that default slot assignment strategy, which is fine for now, where we're just putting things into the first available space, first available slot with space. We are going to update the minimum dwell time though now, and say that things have to spend time in the rack equal to the normal distribution with a mean of 30 and a standard deviation of 5. And that'll keep things in the rack until they're ready to be released. And while we're here, we'll also change the send to port rule so that rather than sending to the first available conveyor lane, we're going to alternate their use by saying that we want to round robin our ports. And so if we watch that run then, so now something stays in the rack for a little while, and then that first flow item will use the first lane, as long as it's actually the first one that leaves. There it goes. And now the second flow item to leave the rack will leave on the second one. And then the third flow item goes out to the third lane, fourth lane, so on. All right, so the next thing to do is to set up the restricted area, where we want to set up an intersection rule for the flow items that go onto the straight conveyor. And so again, if I want to, I can use that selected trick where I can say that these two objects need to be able to do exactly the same thing. They're both going to be entrances to a restricted area. So if I select them both, I can come to my triggers and say that I want to add the on arrival trigger. And so it says two objects changed. And then I'll say that I want to add my area restriction where we say enter restricted area. And then when I click off of that, it says, yep, two objects changed again. So now both of these objects are marked as entrances to the restricted area. And then when I want to turn off that red selection, I just shift click in an empty grid area. So they're no longer selected, so I can treat them as individual objects again. And then on my downstream object, I'll say on continue, maybe just to make it a little bit different, that we are going to exit the restricted area at that point. And again, if we just watch that run for a bit, we'll see the restricted area come into play. So if the area is available, they just get to go. Otherwise, they have to stop and wait for the object downstream of them to clear before they can go in.
Did you have to set like an owner for the exit restricted area?
The exit the restricted area says that the owner is itself. That's why it says current in here. So it's saying that I am the owner of this restricted area. And that agrees with what the entrances say by saying that the owner of the area that you enter into here is current, which is this decision point, out object one, which is that decision point. So each of the entrances recognize the downstream decision point as its owner, and the downstream decision point recognizes itself as the owner. So if you kept everything on the defaults and just made the connections like this, then it just works. All right, now the last thing to do is just to go to the station and say that we have a 3-second processing time, which is pretty simple. And that just means that the flow items are going to stay at the end of the conveyor for 3 seconds before they get released to the sink. And so you'll see them, they'll get there, they'll hesitate, and then they'll continue moving. Okay, now for the challenges, we're mostly talking about things that happen to the rack. So the simple one that we'll do first is to change the use of the output ports so that rather than going round robin, we assign lanes to the different types of flow items. So in this case, I'm going to choose the option under send to port on the rack that says that we will choose a port by case. And again, this is going to be based on type. So we have 4 types. And so types 1 and 2 are both going to use port number 1. So the first 2 cases are already correct. And then for 3 and 4, we're going to say that they always are assigned to port number 2. So that's a really easy way to do this using the port by case option. Makes that pretty simple. And so now what we'll see is that when flow items leave the rack, the red and the green flow items are always on the left-hand lane, and the blue and yellow are always on the right-hand lane. Or vice versa, depending on how you set the port connections. I made my left-hand lane the first output port and my right-hand lane the second output port. So it'll just match whatever port connections you have. Okay, and now the last challenge that said that we want to assign different types of flow items to particular slots on the rack, that is a good opportunity to use our slot painting tool, where we can say that we want to assign slots, or rather we want to assign labels to the slots, and you can name the label whatever you like. Mine is still called slot type from the previous example. And I'm going to say that we've got value 1. And so these 4 slots will be for type 1. These 4 slots will be for type 2. These are for type 3. And then these are for type 4. Now, remember, all we've done so far is we've assigned labels with these values to these slots. Now we actually need to tell the rack to use those labels in order to assign the flow items to a slot. So we do that with the slot assignment strategy that says that we want to match labels for the slot assignment, which again means that we're going to compare the value of a slot label with the value of an item label. And if those values match using that double equal sign, then we are going to allow the flow items to be assigned to that matching slot. So here I just need to update my slot label name to say that this is called slot type, not just type. My flow items label is called type, so I can just leave that one the way it is. And now when flow items want to go to the rack, the rack knows to put things into a particular shelf on the rack that is assigned essentially to that item type. And that just helps our model be more efficient, because now our operator doesn't have to travel as much, right? Because like if you had a type 4 flow item that had to go all the way over to the first slot, that's a lot of walking. But now we keep our backlog of flow items under control a little bit better, because now our operator doesn't have to travel as much.
And where did you set the slot type name to slot type? I caught it when we were assigning slots, but you said,
so
like in our first model. Oh, go ahead.
In the paint slot tool, right? In the properties
Ah.
panel, it gives you the ability to assign the slot name or
That's
the label name. I'm having a
Okay.
hard time saying slot when I mean label and label when I mean slot. Sorry. But yeah,
That's-
this is where you would do it.
Yeah, that's what I couldn't get working a while ago because I was just using the type instead of slot type. All right.
Yeah, and just remember that whatever you choose to name the label up here, right, it can be whatever you want. You just have to make sure it matches down here in the matching labels where it says slot.slot type, meaning that I'm accessing a label called slot type that belongs to the slot, and item.type means I'm accessing a label called type that belongs to the item. All right, so in the last section, the big new ideas that we introduced had to do with the conveyors and the racking objects, and those are a couple of pretty big topics that we really just kind of covered, you know, the basics of how to get started with them. And so, being that those are a couple of pretty big ideas, I want to shift gears a little bit now and talk about something that's a little bit smaller, but still pretty super important. So rather than introducing like a big idea and only talking about some of it, we're going to introduce a more focused idea and talk about a lot of the ins and outs that have to do with it. And that's in describing a tool that is available to us via process flow called the zone. Now, the zone is one of our shared assets that we introduced yesterday. So that means that it has some similarities to the resource that we've already seen, but it also has some pretty important differences. Now, when using the zone, the two things that the zone is primarily used for is to help us gather customized statistics and also establish rules for how tokens are permitted to flow around in our model. So the resource is a pretty rudimentary way of establishing rules where you say that there's a resource that needs to be acquired, and then while you're using it, you own it, and then you give it up and allow another token to use it. A zone is a little bit different in that it is made for multiple tokens to be able to gain access to the zone, but then the zone establishes rules about what kinds of tokens and in what quantities and what criteria are allowed to be in the zone. And we use that similar idea to help us with a lot of stats gathering. Now, the way that the zone is similar to the resource is that it has accessing activities that allow tokens to utilize the zone. And we do that with an entrance and an exit activity, while those are connected to the zone shared asset, so that tokens know that when they enter a zone, they're entering a particular zone, and when they exit a zone, they're exiting a particular zone. So let's take a look at an example of putting the zone together, because again, I find this is easier to show than it is to tell. So I'm going to just make a new model. We don't need the previous example that we already had. And again, the default units are fine. And in my process flow, I'm going to start out with just a couple of simple activities. We'll start out with a source, and that's going to get sent to a delay. And then I'm going to have an enter zone activity. And then I'm going to put in a couple more delays. Just going to throw in a few delays so that our tokens have something to do while they're in the zone. And then I'll have an exit zone. And then I'll just do another delay and a sync. And we'll just connect these blocks together. Now, notice that when you click on the block of activities that has the enter and the exit zone in it, because I don't have a shared asset zone out here, they don't know what zone they're supposed to connect to. So if I bring out the zone shared asset then from the library, I now need to use this exclamation point icon to connect to the zone. And we do the same thing for the exit from the zone, which is a little bit different from what we saw with the resource, where with the release activity, we didn't have to connect it to the resource, but with the zone, we do. With the zone, we have to connect the exit point of the zone up to the zone. Now, if we just hit reset and run, The zone by default assumes that it can hold an infinite number of tokens. So again, this is a way in which the zone is different from the resource. The zone, or rather, excuse me, the resource assumes that only one token can use a resource at a time, and it's up to you to adjust that that count value up in order to allow multiple tokens to use the same resource. With the zone, we assume that you want an infinite number of tokens to be able to go into the zone, because the primary use for the zone is to gather stats. And so the entrance and the exit from the zone here is established to allow you to say that while tokens are in between the entrance and the exit, I'm gathering stats about what the tokens are doing only within this section of the model. Now, normally activities gather statistics about themselves, just like the objects gather statistics about themselves. But the zone adds an extra layer onto the model that allows me to say that I'm interested in what the tokens are doing between this event and this event, between the entrance and the exit. So how do we gain access to those statistics? Well, if you click on the zone, and again, you can do this either from the properties panel up here or from the drop-down menu below the activity. There's a button here that allows you to open the statistics. And if you click on that, this will open up a basic window of stats that the zone is gathering. So over here, we have our, I'll just stop it. We have our throughput-based stats for our input and our output. So our input here says that the zone has received 135 tokens and it has released 124 tokens. Currently, it says that there are 11 tokens in the zone. Our minimum number of tokens in the zone was 0, our maximum was 17, and our average is 9.48. So really kind of similar to the stats that we've seen on the objects and things like that. But now, rather than being individual stats for like one of these delays, it is a cumulative set of statistics for what the tokens are doing between the entrance and the exit. And so one of the nice things about the zone then is that by changing where the entrance and the exit points are, you can change the boundaries of where the statistics that you're interested in are being gathered. And since the zone assumes infinite capacity by default, it really is just a way of saying, I want to know what the tokens are doing as they flow between these delays. Now, so far, these statistics are no different from the stats that you can get from a resource. The resource has the exact same set of stats, but what we're going to see in a little bit is that the zone goes well beyond the kinds of stats that can be reported by the resource, which is one of the reasons, again, why it exists. Now, below the regular stats like input, output, content, and stay time, there are another set of statistics called request stats. And so the request stats have to do with tokens that are requesting access to the zone, but their requests haven't been fulfilled yet. So right now, the only request-based stats that are active are request input and request output. So kind of imagine that there is a request queue that the zone manages about tokens that want to go into the zone. And right now, the request input just means that there have been 135 requests made on the zone, because those are requests that have been made on the zone. And then the request output says how many requests have been fulfilled on the zone. So right now, the input to the zone is the same as the request input and the request output, because as soon as a token requests access to the zone, it is immediately granted, because currently there are no restrictions about how tokens are allowed to access the zone. It's assumed infinite capacity. So as soon as a request is made, it's immediately fulfilled. So that token enters the request queue with the request input. It exits the request queue with the request output, and it becomes input into the zone with just the regular input stat. Okay, now the other request-based stats are only active if there are requests that are waiting for their turn to access the zone. So what happens if we add a little simple restriction to the zone? Well, we can do that by coming to the zone properties. And again, you can do this either way. And there is a checkbox that allows you to create a maximum content on the zone. And so if I fill in a value here, like let's say that we've got 3, a maximum content of 3 here means that only 3 tokens are allowed to be in the zone at the same time. So if we run the model now, as our tokens progress and we get 3 tokens that are in the zone, additional tokens request access to the zone, but those requests are now pending as we wait for additional space to become available. So if we stop the model, note the use of the red and the green dot numbers over on the zone shared asset itself, where it says that we have 17 pending requests on the zone, and we have 3 active tokens in the zone. And that's also borne out by looking at the request-based stats, where it says our request content now is 17, which matches up with the red dot number. Now, in addition to the content, we can also look at the request stay time, which tells us how long on average, or minimum and maximally, how long it takes for a request to be fulfilled on the zone. So the minimum time spent in the request queue is 0, which makes sense because some tokens arrive and they're immediately granted access, so they spend 0 time in the request queue. Our longest waiting token so far is waited 36.29 seconds, and our average time spent in the request queue is 16.2 seconds. We can also see that with the request content, where it tells us the min, max, and average number of tokens in the request queue. And we can also see now that has a different effect on the relationship between our request input, request output, and our input, right? So there have been 25 requests made on the zone, 8 fulfilled requests, which means that 8 tokens have been granted access to the zone so far. And you also notice that using the thumbtack icon that we mentioned on the very first day, you can use this thumbtack option to create simple charts based on any of these statistics on this window. Okay, any questions at all so far? Okay, so right now, with what we've gone over with the zone, the amount of overlap between the zone and the resource is pretty high, right? Using the maximum content feature of the zone is very similar to just updating the count of a resource to increase the number of tokens that are allowed to access the resource. And the statistics that we're gathering over here on the zones panel is also the same kinds of stats that the resource can gather. So again, why do we have 2 different ways of doing this? Why is there the zone and why is there the resource if what we're seeing so far is that there's so much overlap? Well, from here on out, we're going to be talking about some of the advanced properties of the zone that allows us to really differentiate the kinds of stats that we can gather and also the kinds of restrictive rules we can enforce. And we gain access to these abilities of the zone by going to the zone properties and clicking on the button that says more properties. Because there's so many things that the zone can do, we couldn't put it all in the right-hand panel. And instead we have a separate window where we can manage these things. And so the first additional stats gathering tool that we're going to take a look at is related to what we call partitions. Okay, now a partition is a way of creating different populations of tokens that, while in the zone, they form stats gathering categories. So you can establish a partition mechanism or a partition scheme that allows you to say that tokens that have this value assigned to them are going to be placed into a particular partition. And then that partition becomes a stats gathering group that allows us to say, I want to see the stats in the zone for things that are in partition A, or things that are in partition B, or things that are in partition 5, right? Whatever value you indicate as the partitioning scheme becomes the partition ID that the tokens will be organized into. Now, this doesn't change anything about the way things work visually in the execution of the tokens as they flow through the zone. It just changes how we can gather stats about those tokens. So in order to create partitions on the zone, we need labels. So I'm going to drag out an assign labels activity. I'm going to put it right after my source here. And I'm just going to create a label. Whoops, didn't mean to do that. I'm just going to create a label called type. Or if you wanted to, you could also call it partition ID. Doesn't really matter what you name the label, right? We're just saying that this label is going to be used as my partitioning mechanism so that tokens that have a shared value for this label are all organized into the same partition as far as the zone stats are concerned. So I'm going to say that the value is going to be assigned just randomly. I'm going to say that, no, I don't really want to use the uniform. I'll use the by percentage option. And we'll say that we have a 50% chance to assign a value of 1, a 30% chance to assign a value of 2, and a 20% chance to assign a value of 3. So this means that my partition ID will have values 1, 2, or 3, right? And these are the percentages that they will occur. Now on my zone properties, I'm going to say that we are going to partition the tokens according to the token label called partition ID. And again, just remember that the name of the label can be whatever you want. I just called it partition ID for a little bit of clarity. So whatever value is stored in this label, that becomes the partition that the tokens will be organized into. Okay, so if we say okay to that and run the model doesn't appear to be running any differently, right? Because remember that the partitioning scheme that we've talked about doesn't change the way things flow. It just changes what kinds of stats we can report on. So if we open up our stats window, notice that the stats window doesn't say anything about partitioned stats. It has some stuff about unmatched that we'll talk about later on, but it doesn't have any listing of my partitions in this window. So if we have these partitions, how do we actually report on the stats for the tokens that belong to these different partitions? Well, this is where we need a dashboard. So we're going to create a dashboard window. I'll just drag it over here. And in my dashboard template library, there is a section dedicated just to zone statistics. So if you want to gather any of the special stats that the zone has the capability of reporting, you need to start with one of these two templates. You either need to start with the regular zone statistics or with a chart template that knows how to work with partition-based statistics on the zone. So since we're working with partitions right now, I'm going to reset my model so that the clock isn't running. And I'm going to say that I want to start with a zone partition stat. So it's going to give me 3 different visualization choices. I can either visualize the stat with a bar chart, a line chart, or a table of values. So I'll do a line chart for this one, and I'll just click that into my dashboard. Just make it a little bit bigger here. I don't know why that. Okay, now this chart has a set of options on the right-hand side. And for any of these zone-based charts, the first thing that you need to tell the chart is what zone to look at for the stats gathering part of the chart. So since these stats are being gathered by this zone right over here, I need to use my eyedropper and say that we're gathering stats out of this zone. And we need to differentiate that because you could have multiple zones in the same model, all doing different things and gathering different stats at different points. So this is just there to say, hey, this is the zone's stats that I care about. I want to look at this particular zone, not this other one or this other one that you might have in your model. And then from the drop-down menu, we see a listing of different statistics that the chart can display. Now notice that these are all partition-based stats because again, the template that we chose deals with partition-based stats. And let's just look at the default one, the very first stat that just says partition content. Okay, so if I hit reset on this, it draws me my line chart. And then when I run, I'm going to get a different line for each partition in the zone. And it looks like I set something up wrong. So let's do that again. Partition content, it's a number. Did I forget to actually say okay to that? No, partition ID, that's okay. Why isn't it drawn? Let's try to view status and make sure that the partitions are being populated. Okay, so in the zone status window, it knows that we have partitions 1, 2, and 3. So that information is getting gathered correctly. But for some reason, it isn't populating my chart. Oh, okay, there we go. Interesting. So it looks like there might be an issue with this drop-down menu where you have to actually select something even if it is already selected. Because I just went to the drop-down menu, didn't actually choose anything from this list. I just clicked off of it. And so when I went back to it and clicked on the actual option in the drop-down menu, it looks like it captured that correctly. So that could be a bit of an interface bug. At least it looks like one to me. I'll have to report that. But anyway, so if you actually choose the stat from the drop-down list now, what is this actually showing me? Well, just to contrast, let's take a look at the regular content stat. Whoops. That we can get from the zone window. So I'm going to go to the content stat and say, let's pin this to our dashboard as well. So both of these charts are going to show me content change over time. Oh, actually, this looks bad too, because I'm going to take the maximum content off. I forgot about that. Uncheck maximum content. Okay, that looks a little bit more interesting. So the content versus time chart down here is showing me the change in the population size in the zone for all tokens, right? So the line here peaked out at about 17 tokens in the zone, and so you lose tokens, you gain tokens, that forms the stair step graph. But the partition-based version of this chart is showing me that at this point, right around 801, right before that time, so right here, we had 10 tokens that were type 1 that were in partition ID 1, and we also had 5 tokens that were in partition ID 2, and we had 2 tokens, it looks like, that were in partition ID 3, right around that same time. So this chart is showing me the breakdown of what tokens belonging to which partitions are in the zone over time, whereas this chart is showing me the change in population for all tokens as a single statistical category. So the partitioning mechanism is allowing me to separate out populations of interest, so I can say, well, I'm really only concerned about the stats associated with partition 1. So here's the chart for partition 1 following that blue line. Or here's the chart for partition 3, so I'm only following the orange line. And again, contrast that with the total population with the standard content versus time chart. Okay, so the tokens that have this label assigned to them for the partition ID is what indicates what partition they should belong to. And that automatically allows the zone to report those statistics to one of these charts. So in order to gain access to these partition-based stats, all you need to do is have a label that indicates what partition token should belong to, and also a chart that knows how to look at those partitions and display those values based on the chart that you want. Visualizing things either as a bar chart, a line chart, a table of values, and then making sure you set it up over here on the properties for the chart. Any questions there at all so far? Okay. Now, another mechanism that we have to, again, help us gather more customized stats also relates to creating populations of tokens that we can report stats about. But rather than putting things into rigid partitions, we can put them into more fluid subsets. So a subset is another way to define like a subpopulation of tokens in a zone for the purposes of stats gathering. But the way that we define subsets is a little bit more loose compared to partitions, because partitions are pretty rigid, right? Because you have a value that we assume all the tokens have assigned to them, in this case, the partition ID. And we're saying that whatever value is in their partition ID, that's the partition that they're in. You can't simultaneously occupy two partitions, and you can't change partitions once you enter the zone, right? If I were to have an assigned labels activity inside the zone boundary and change from partition ID, say 2 to 3, the zone isn't going to see that because it only notices what partition you should be assigned to as you enter into the zone. So partitions are very rigid in that way because we're saying, hey, whatever value you entered in on or entered in with, that's the partition you belong to. And like I said, you couldn't have two competing values for partition ID that might put you into two different partitions. Subsets, however, rather than being assigned based on a single value, are assigned based on a set of criteria that can be met, which means that a token could simultaneously belong to multiple subsets and count towards the population of multiple defined subsets. So let's look at how we define subsets. First, I'm going to create another label. I'm going to say that we've got a label called weight. And I'm going to say this is defined using the uniform distribution so that we have a weight range of 10 to 50, and we'll call it pounds. Okay, so in my subset definition, I can give my subset a name. I'm going to call this subset heavy tokens. And then right below that, I have a selection criteria that allows me to assign tokens to some criteria, or assign tokens to the subset based on this criteria. And so if I type in weight like this, that means that the weight label of the tokens is going to be applied as one of my selection criteria. But the weight label by itself doesn't really tell us anything. It just says, okay, weight. But then I can add other operations like my comparison operations, like greater than, equal to. And say with this criteria, I'm saying that the tokens whose weight label values are greater than or equal to 35 will be members of this subset. Okay, so let's make a chart that displays the content of our heavy tokens. So I'm going to again go to my dashboard library, but this time I'm not interested in creating a partition-based chart. I'm going to create a regular zone stats chart. And this time I'm also going to choose a line chart so we can compare the versus time graph. Just make this a little bit larger. And again, on my chart properties, I need to direct this chart to look at the zone for the data source on these statistics. And then on the drop-down menu, I have an even larger set of statistics that I can choose from. Now, notice that we have our regular stats, content, input, output, and stay time. Those are the stats for the zone as a whole. We have our request-based stats, also for those stats that represent requests on the zone. These first set of stats represent the same stats that you get from the stats window on the zone. Okay, so these 8 stats are all also available to you here to be viewed. Now, beyond that, we start getting into some more interesting base stats. So, for example, the subset set of stats allows me to report on statistics only for given subsets of my zone. So let's look at the subset content. Subset content means that I can display the statistics only for tokens that meet this criteria. And so the subset that I have defined on the zone right now is only the heavy token. So I'm going to select that. And when I hit reset and run, this line chart now only shows me the stats for the heavy tokens. And the tokens that are heavy are the ones that I defined that say that they have a weight of either 35 or more. So again, compare the difference between the three charts here, where the partition-based stats is giving me the content change of the zone for each individual partition. Content versus time is telling me the content change for the entire population of the zone. And now this chart is only showing me the population change for tokens that meet the heavy criteria that I assigned in the subset tab. Now you can do some pretty cool things with these selection criteria. Like for example, if I make another subset and say, okay, I'm interested in tokens that are either partition 1 or partition 3. Maybe I want to gather a statistic only for things that are in partition 1 or in partition 3. I want to treat that as a single category of statistics rather than like seeing only the stats for partition 1 or only the stats for partition 2. That means in my token selection criteria, I can say partition ID, because I'm looking at the label that I called partition ID, and say that partition ID has to equal 1 to be a member of this subset, or partition ID has to be equal to the value of 3 in order to be part of this subset. I'm just realizing I spelled that wrong, so just to minimize my mistakes, I'm going to copy and paste that. Okay, so again, note the token selection, the selection criteria here that says that this label the label value of the tokens can either equal this value to be a member of this subset, or it can equal this value to be a member of this subset. So you can use logical ORs as part of the selection criteria here to say that either of these values can be true and have you be a member of the subset. Right? And so that's defined with a logical or instead of a logical and, because if you put in an and here, that would mean that the partition ID label would have to simultaneously be the value 1 and 3. So for each individual token, you'd be saying that in order to be part of this subset, partition ID has to equal 1 and it also has to equal partition 3. Right? So that's why it's an or, because this criteria is evaluated for each individual token. So if we look at something's partition ID and says, do you equal 1? And it says no, it says, okay, well, do you equal 3? And if it says yes, then okay, you're a member of this subset. Right? And so now I can create a chart for that as well. Again, this would be a regular zone statistics chart because it isn't based on the partitioning scheme, it's based on the subset scheme. And so if I create a chart for that, again, using a line chart, I can say I want to gather stats from my zone. The stat that I want is a subset content, but this time the subset that I want to display is for things that meet the partition 1 or 3 subset. So if we hit reset and run. So again, this chart is now as if I'd combined the line charts for the blue line and the orange line into a single chart on this subset definition. So I can treat the things that would be assigned, the things that are assigned to partition 1 and 3 as a single statistical category instead of 2 different statistical categories, which is what the partitioning scheme does. Does that make sense? Anyone have any questions on that so far? Okay, so again, the one of the main ways that the zone helps us gather these custom stats is to make it easier to define populations of tokens whose stats we're interested in. You know, so if we want to gather stats only about heavy things, or we want to gather stats about things that are assigned to either partition 1 or partition 3. Excuse me. And you can even you know, combine these different ideas. You could have a subset that says, you know, I'm interested in things whose weight is greater than or equal to 15 and whose weight is less than or equal to 35. So only things that weigh between 15 and 35. So that could be like one selection criteria. And then you could also say, and partition ID equals 2, right? You can get really, really specific with these, right? So you're saying, I only care about, I want to report stats for things that weigh between 15 and 35 and also belong to partition 2. Right, so these subset definitions can get really, really particular, so that you can really drill down on different criteria of tokens and report stats on them. Allows you to do some pretty neat things. We call that like partition 2 things that weigh between 15 and 35 pounds. And so you would define this kind of natural language subset definition with this kind of syntax. Okay, now all of the stats that we have displayed so far, whether we're talking about the partition-based, total content, heavy things, partition 1 and 3 together things, all of these stats are in terms of the number of tokens, right? So like when we get to this point, the y-axis value 8 represents that we had 8 heavy things in the zone, and then we had 7 things, and then 6 things, and then 5 things for a long time. Then we went back to 6, then went back to 5, back to 6 for a little bit, and then back to 5, right? And so as we follow the change in content, the y-axis is telling us how many tokens meet the criteria over time, right? Now, again, one of the cool things that the zone allows us to do is to change what those statistics could be reported as. So I'm just going to make a separate dashboard window. Separate dashboard window. And I want to introduce something that we can add to our partitions and our subsets to enhance our stats again. And that's what's called a calculation. Now, a calculation is essentially a way to change how the y-axis value, or rather change what the y-axis value of the charts represents. So before, all of our y-axis values were in terms of how many tokens. But the calculation allows us to display the y-axis value as an amount of material. Okay, so if we come to the calculation section here, this means that if I add a calculation, we're adding this calculation only to this subset, right? And then if you go to the partition tab, you can add calculations just to your partitions as well. So a subset is going to own this calculation, and the calculation name is always total something, because what the calculation does is it looks at some label value or arithmetic expression and sums up that value for all the tokens in this subset. And then the charts allow us to display that value in different ways. So like, for example, if I were to go to total label value and say, okay, I'm interested in the total weight of my heavy tokens, and we can find weight data assigned to the tokens in the label called weight. Okay, so on my dashboard window now, I'm going to create, again, a zone statistics-based chart. Oh, wait, I dragged out the wrong one. I want this to be a line chart again. And again, the zone that we're gathering data from is here. But then under my statistic, I'm going to say that I want to display a calculation-based stat. And I'm going to choose calculation total here. And actually, I'm going to bring this window over here to the side just so we can compare. Because I want you to compare this chart against our heavy content versus time chart. Okay, so we chose calculation total from the statistics list, and then we have to choose the combination of subset and calculation that we want to report on. So right now I only have one subset that has a calculation, and that's my heavy tokens and total weight combo. So I'm going to choose that from my drop down. I'm going to rename this chart. Well, actually, I'll do that later. So now when we hit reset and run, and I'll just stop it here. Compare these two charts. How are they similar, first of all?
Shape is identical.
Yeah, the shape is identical, right? But again, notice the y-axis value. So the chart on the left represents how many tokens are in the zone. Like, again, let's take a look at where we topped out at 8 tokens. At that same point of the curve on the other chart, the y-axis value is over 300. So what does the y-axis value represent over here?
Some of the weights.
Yeah, it represents the weight of those heavy things. So in both charts, the thing that we're concerned with, or rather the population of tokens that we're concerned with, are the heavy tokens. But rather than counting how many tokens there are, this chart is telling me how much those heavy tokens weigh. So the change over time here isn't in the population size, it's in the amount of material that that population represents. So where we peaked at 8 tokens that are heavy, that meant we had upwards of about 370, 380 pounds worth of material. And so when we came back down here where we had 5 tokens at this point of the curve, that represented a little over 200 pounds worth of material. So it's a different way of interpreting the stat. Rather than interpreting it in how many tokens meet this criteria, it's telling me how much material those tokens represent. So if you have any models at all that think about your statistics, rather than thinking about them in terms of discrete entities, but rather an amount of some material or some cumulative value, the calculation-based zone stats should be very exciting. Because this was something that prior to having the zone, we didn't have a good way to do this. You would have to do the math for this yourself. You'd have to have like a custom stats gathering mechanism that looked at a discrete entity like a token or a flow item and took the amount that they represent and added it to some cumulative value. Like every time something like entered or exited, you would have to manage incrementing and decrementing that value. But here, the zone just does it for us by setting up first a subset that allows us to define the membership of this subset, and then also a calculation that allows us to display the stat in terms of this cumulative value, as opposed to how many tokens there are. Just a different way of considering it. Okay, does that make sense? Does anyone have any questions there? Okay. Now, in the slide presentation, I don't have any slides that talk about the things that we just did. But if you look in the download set of materials, there's a model called the zone walkthrough that walks through each of those different aspects of the zone that we just did as a demonstration. So if you want more information about subsets and partitions and calculations and all that stuff, I'd invite you to take a look at that model and observe the different examples in that model and the documentation that I put into the process flows there. All right, so this is a good natural breaking point. We can go ahead and take our hour-long midday break. Let some of this sink in, and when we come back, I'll turn you loose on an exercise that incorporates all this stuff about the zone. Okay, folks, welcome back after the break. So since the next thing that we're going to do is just to jump right in and build a model using what we learned about the zone. So sharing my screen right now, and the slide that we have up is describing the model that we're going to build. Just for simplicity's sake, this is a model that we'll build just entirely with process flow, so we're not going to worry about any objects implementation here. And the main thing that we're going to want to take away from this is the ability to use the zone as both a stats gatherer, as defined in the output section of this, and also as a means to help control the flow of our models. And I'm just realizing now that I think I forgot to mention how we can use the things that we talked about, like subsets and partitions, as a means to control the flow. Yes, I definitely did not tell us about how to do that before the break. So just really quickly, I want to point out before we get into that everything that we talked about in the zone to this point was all centered on gathering stats, right? So we define things like subsets and partitions and calculations in order to help us create different charts and give us access to different outputs that would normally be hard to get. But one of the other things that the zone is really useful for is to control the flow and establish rules about what kinds of tokens are allowed to flow through the zone. And this is where the other tabs on our more properties window is going to come into play, where we have subset constraints and also partition constraints. Now I'm going to focus mostly on the subset constraints, because if you understand how to use the subset constraints, I think the partition constraints are pretty easy to figure out after that. So the idea behind subset constraints is to be able to take things like the subsets that we defined over here and to be able to say that we want to add constraints to them. It's like, for example, if we take a look at our subset that includes our heavy tokens, you can do things like say that the number of tokens in this subset has to be limited to some value. So where it says that the calculation is based on the number of tokens, if we were to say 5 heavy tokens, that means when our model runs now, we will occasionally see unfulfilled requests on the zone due to the excess of heavy tokens. So I'm just going to see if I can get lucky and stop it where that's happening. So here's an example of a token that's being kept out of the zone. And if we click on it, we can see that it is part of our heavy subset, because our heavy subset's defined as things whose weight is 35 or more. This weighs 37.63. So there must be 5 other heavy tokens already in this zone. So how can we verify that? Well, if we go to the zone properties and say view status and go to the subsets tab, we can see now that there is a limit column on this window that says that our heavy tokens are currently at 100% of limit because the current content of that subset is 5. Now that doesn't mean that other tokens are kept out. It just means that this one heavy token is kept out because it would violate the constraint that we set that says that we can only have 5 heavy tokens in the zone. And as an added cool thing that we can do with these constraints is that we can also base the constraint on a calculation. So rather than limiting the number of tokens to the zone to a number, we can limit the amount of material in the zone to some calculated value. So like in this case, I could say that the total weight of the zone is not allowed to exceed 600. And remember, this is associated with the heavy token. So this would mean that we have to keep the amount of heavy material that meets the heavy token criteria below this value of 600. And we're able to do that because our subset has a calculation assigned to it. So if you have a subset, you are allowed to limit how many tokens of that subset are allowed to be in the zone, either by limiting the pure number of tokens or by limiting based on some kind of a calculated value, some sort of a cumulative label value that the members of that subset have assigned to that. Okay, and again, that's the sort of thing that goes beyond just the simple maximum content that just limits the total content of the zone to some number of tokens. But here we can add different controls to different subset populations based on these criteria, either the number of tokens or a calculated value. Does that make sense? Does anyone have any questions on that?
Seems reasonable.
So in our model that we want to build, we are just going to model an abstract representation of like a factory where parts are produced by a source activity. And then we want to assign them these different label values to represent different attributes of those parts. So we're going to assign our tokens a dollar value label that can range from $100 to $1,000 using the uniform distribution. We want to assign them a weight label that ranges from 10 to 50, also according to the uniform distribution, and a type label that can be a value from 1 to 5, but are broken down or distributed by these percentages. So 40% for type 1, 30% for type 2, and 10% for types 3, 4, and 5. Now on our factory floor, we just want to send our parts to a delay. So we just want to send them to a delay according to their type. So what I would like you to do is to send your tokens to a decide activity, and then let that decide activity choose which delay to send the flow items to, or not flow items, sorry, tokens. What delay to send the tokens to. And mostly that part is to get some additional experience using the decide activity. I just want you to get you guys some more practice using the decide options. And so even though all the delays are going to have the same delay time, the same distribution, it's fine. Just create the 5 separate delays, 1 for each type, and then use the decide activity to route tokens to the correct delay for their type. Now on the third bullet point here, we want to use the zone's constraint capability, where we want to set up some rules that says that on the factory floor or across all of the delays that we have, we can only have 10 tokens in progress at a time. And only 5 of those 10s can be either type 1 or 2. And only 3 of those parts can be classified as heavy. So you can have 10 total things. And then of those 10, only 5 can be types 1 or 2. And of those 10, only 3 can be heavy. And we're defining heavy as those tokens whose weight label is 35 or more. And then we have a section of outputs where we want to use the zone statistics gathering capabilities to display some different stats. Like we want to know the total weight of all the heavy parts on the floor. We want to know the total dollar value that have been through the factory. So like what's the total revenue of the factory by counting the dollar amount that every token is carrying with it as they leave. We want to know how long on average types 1 and 2 wait their turn to be processed. And we want to know the total value of expensive parts as they wait to be processed. And we're defining expensive things as any token whose dollar value is $800 or more. Now, to kind of help out with these stats, on the following slide, I have a short description of what each of the stats in the zone chart drop-down option mean. So you have a listing of all the individual stats and also a short definition of what they display. So hopefully, taking this together with the description here, you'll be able to figure out what stat you want to report on from the zone. and how you have to configure the zone to support that statistic. Now, as far as the description goes, this is just a simple flow chart of what your model might look like. Where first we'll have a source that creates our parts. We have an assign labels activity where we will assign our dollar value, weight, and type. And then we'll use the decide activity to route things to a particular delay according to their type. And while our tokens are in one of these delays, they're considered part of the zone's content or part of the zone's population. And once those delay times are over, then that's the end of the process and the end of the model. And then we just want to show the outputs from there. Okay, any questions at all? Okay, so this one will take a little bit of time. This one usually takes probably about a half an hour or so. I would recommend starting like one bullet point at a time and just kind of test and verify as you go along. Make sure you can do all this, all these pieces, and then we'll just plan to do the walkthrough in about 25 or 30 minutes, depending on how things go.
Alrighty, well, let's get it.
All right, good luck. So to do the walkthrough on this one, like I said, this is one that a lot of people tend to struggle with. I think the output section in particular tends to feel a little more difficult than some of the other models we've done, mostly because you have to really think about what the stat is asking you for and then try and figure out what stat that the zone can give you is going to be the right one to choose. So we'll just start with a clean slate. And since I don't need the 3D part of this, I'm just going to close the 3D window. So I have just my big process flow. And the first thing that you would do is just, again, to create a source to generate your tokens. Now, we didn't say anything about what the arrival rate should be. So the default arrival rate for this is just fine. But our second step is going to be to assign labels. And so we need to assign labels that will tell us the type, the weight, and the dollar value. So again, remember, this is something that I like to do with a lot of my activities where I'm just including like some documentation. So I'm assigning labels that are called this. And my first label here will be type. And we said that we wanted the value to be assigned according to a set of percentages. So we're going to say we want the value assigned by percentage. We'll say 40% gives me a value of 1, 30% a value of 2, and then we'll do 10% for 3, 10% for 4, and also 10% for 5. And then I need another label that tells me how much these tokens weigh. And this will be assigned using our uniform distribution with a minimum of 10 and a maximum of 50. And then for our last label, this is going to tell us the dollar value associated with this part. And this will also be assigned using uniform with a minimum of 100 and a maximum of 1,000. Okay, is everyone okay with that part so far? Did everyone get hung up on the labels? Okay. Now I'm also going to take this time to use my more properties of my process flow to assign the colors of my tokens according to the type label, so that my type 1 tokens will be red, 2 will be green, 3 will be blue, 4 will be yellow, and 5 will be orange. And that's all handled for me automatically by the token color section under the visualization options for the process flow properties. And then I need to have a decide. And I'm just going to say this is going to be called decide by type. Whoops. And then I'm just going to create some delays. So I'm going to have a delay here that I'll say this is delay for type 3. And the scale value here is 45. I'm just doing that to save myself a little bit of time. I'm just going to copy these and give them different names. Here in just a second. Actually, that's too close. So this will be for type 1 tokens. This will be for type 2 tokens. And this will be for my type 4 tokens. And then for my type 5 tokens. So I'll just make connectors over here. And of course, it doesn't really matter what you make this look like, right? I mean, I'm just kind of trying to lay this out in a way that's somewhat easy to follow. And then once those delay times are over, that's just the end of what I need the tokens to do. So I'll just send them to a sync. So I haven't brought in the zone yet. We'll worry about that in just a minute. So before I test to see kind of where things are out, I'm going to set up my decide activity to say that we will choose a connector by case. And my case function is going to be to use my type label as my decision-making variable. And then all of my type 1 things will go to connector 1, then 2, then 3, then 4, and then 5. If we just test it now, when we hit reset and run, nope, my colors aren't happening. So what I do wrong, I forget to say okay. Looks like yes, I forgot to say okay. And so now my tokens are colored in. And so what we should just see here then is basically that the same color tokens are all going to the same place in terms of what delay they go to. And like I said during the description, this is mostly an excuse to get some more experience using the decide activity. I haven't seen it in a little while, and it's always good to remember that we're allowed to make these kinds of decisions as a flow is executing. So just doing that as an example. And if we take a look at some of these tokens, like we look at this green one right here, we can see that it's type 2. We can see what its weight is. We can see what its dollar value is. This blue one also has type 3 and a weight and a dollar value. Right. So we're just, each of these tokens just carries this information about itself, where we know what type it is, we know how much it weighs, and we know how much it's worth. Now, the next part of the model description says that we need to enforce rules about what kinds of parts are allowed to be on the factory floor at a given time. And so we need 10 total, 5 that are either type 1 or 2, and 3 that are heavy. Now, for the first rule, there are 2 ways that you can go about doing it. The way that most people do it is to say, okay, well, we've got our zone. And I'm going to insert an enter zone activity right before the decide activity. And I'm going to get an exit zone activity right before the sync. And I'll just use the exclamation point to attach them. And so the first way that we're going to see to enforce the limit of 10 total parts in progress, the first rule that we need to follow, the easiest way to do it is just to say use content or use maximum content and limit it to 10, right? And so then when you run it, you should see that that's enough to keep a limit of 10 tokens going through this part of the model at a time. Like, see, there's a couple of requests that are waiting their turn to get into the zone, where we can see that we have 10 active tokens and 7 requesting tokens waiting their turn to go into the zone. Okay, so that's the first way to do it. The other way that you could do it would be to use a subset. where you could come to the subset definitions and say that we want a subset that we call all parts or something like that. And the default selection criteria says that we will include all tokens. And so if we include all tokens in the subset, that means that there's no, like, the entire population of the zone is the subset. And that means that I can set a subset constraint on that that says that all parts are now limited to up to 10 tokens. So that's a few more steps, but it gets us the same thing as the maximum content. So usually right now, people ask, well, why would you bother doing it this way if you can do it with just the checkbox and the maximum content? And the answer to that is going to come when we start looking at some of the outputs from the model, where having a subset is preferable depending on if this subset of all tokens is a set of tokens that we want to report something about. Because we can't add any of our special stats gathering tools to the maximum content aspect of the zone. We can only do that with things like subsets and partitions. So if you're just creating a limit for the limit's sake, then using the max content is fine. But if you need to do anything more complex with it besides just creating that limit, then it might be better to do it as a subset. And like I said, we'll see an actual example of that in just a minute.
So I did it a third way, and I want to know if it's like outright wrong or not.
Okay.
If it'll work in the end. I'll share in a second.
Yeah, go ahead.
So I put an enter zone at each of the delays right here and an exit zone here, and all of these tie to the zone.
Yep.
Is that okay?
That's fine. Yep, you can do it that way.
Okay, cool.
Yep, perfectly fine. Okay, now for the other limits that we need to put on the zone, for these we have to use subsets because we're defining a subset of tokens that meet certain criteria, and we want to add constraints to those subsets. So back over in our model, I'm going to add another subset, and I'm going to call this one my heavy parts. And my selection criteria here is to say where the weight label is greater than or equal to 35. Right, so that satisfies this part of the description that says that heavy parts are classified as being 35 or more. And then to constrain the zone on how many of those tokens are allowed to be in the zone, again, we go to the subset constraints, and I'll say that the heavy parts are now limited to 3. And then for my last subset, I'll add a third subset, and I'll call this combined types 1 and 3. Because remember, the name can be whatever I want, whatever makes sense to me. And then in my selection criteria, we're going to say where the type label is equal to 1.
I think it's only parts 1 and 2.
Oh, is it 1 and 2? Sorry.
Yeah.
Okay. Yeah, 1 and 2. So where type is equal to 1, or where type is equal to 2. So this is really similar to what we talked about during the lecture portion, the lead up here, where we're evaluating the token and we're seeing if either of these expressions are true. And so if either of these expressions are true, that causes the token to be added to this subset. Now, one thing to look out for when you're using things like ors and ands is I've seen some people do this where they say where type is equal to 1 or 2, and they think that's going to work. But see, this is a very human way of expressing this idea, because in context, humans understand that we're saying where type is equal to the value 1 or equal to the value 2. Computers aren't really good at making that kind of inference. Instead, what the computer thinks you're saying is where the expression where type is equal to 1 is true, or where the number 2, without any kind of context, is true. So this may give you some strange results. It's not going to be an error because it's perfectly fine to say, does the number 2 exist? But we're not actually associating the number 2 with a possible value of the type label of this. So you'd have to make sure again that we include the entire expression that says we want to know if this is true, where type is equal to 1, or if this is true, is type equal to 2. Okay, and then same thing again, we can take that subset, go to our constraints tab, and say we want to limit how many of these we have to 5. And so again, now if we run the model, we'll see that there are even more possibly waiting tokens because we've created additional constraints. So like, for example, here we've got a token that is waiting. There's only 5 total tokens in the zone. So we might want to figure out, okay, which constraint would this token violate? So if we open up our status window, we can see that our all parts, we're way below our limit on all parts. We're 50% of limit here, but our heavy parts, we are at 100% of limit. There are 3 other heavy parts in the zone right now. And if I want to know who those tokens are, I can go to the subset tokens and see that my heavy parts are tokens that are at the type 4 delay, the type 1 delay, and the type 5 delay. So it's this one, and one of these are considered heavy. Which means this token can't enter because it is also heavy, and that would violate our constraints. And so as we continue to run, as more space becomes available, tokens are allowed to leave the request queue. Again, we're at a point now where we are below our total maximum limit, but there is some other constraint that is keeping the tokens out of the zone, which is what we would expect because we have 3 different rules at work here, and we are trying to make sure that we don't violate any of them. Okay, any questions at all? Did anyone have any trouble getting to this point?
This is where the trouble started for me. The next step.
Yeah, doing the outputs.
Yeah.
Yeah. Okay, so if there's no questions then about how we got here and what everything means, then we'll go on to the part that usually trips most folks up. And that is doing the output. So I'm just gonna kind of like put the model off to the side a little bit because I don't really need to pay super close attention to it anymore. And just for screen real estate purposes, I'm just gonna make a couple of dashboard windows. Okay, so let's take a look at that first stat that the slide is asking us for, where it says, what is the total weight of all the heavy parts currently on the floor? Now, we actually did a version of this during the lecture. And what we want to get essentially is the number of tokens that meet the heavy subset in the zone. Right? We only want to know how many heavy tokens there are. So that means that that is going to be a content-based stat that is based on our heavy subset. So we start by creating a chart. So I'm going to go to my dashboard library. I'm going to grab the zone stats chart. And the first choice that I have to make is which way I want to visualize this stat. And just because I like line charts for this one, I'm going to choose line chart. We'll click that up here. And I'll use quite a lot of screen real estate here to draw that chart. Okay, so the chart by itself doesn't do anything. The first thing we need to do is tell it that we are gathering stats from our zone. And then from the stat drop down, we need to choose which stat is going to display the content of the heavy token subset. So that means we're going to go to the subset section of the statistics menu, and we're going to choose the subset content. And then in my subset calculation dropdown, I have 3 different subsets. So I need to make sure that I choose the right subset. Do I want to report on the subset content for all the parts in the zone, only the heavy parts, or only things that are types 1 and 2? So in this case, we want heavy parts. I'm going to choose that. And then if we hit reset and run, I'll rename this chart as well, call this heavy content. Actually, I won't be able to change it while the model is running. So we'll just watch the model run for a little bit. And we see that we reached a point where we had 3 tokens that meet the heavy criteria, and then we lose one, and then we gain one, and we lose one, and we gain one. Because we have a limit on how many heavy tokens we're allowed to have, we should never see this line go above 3. Because this is only showing me how many heavy tokens I have in the zone at any given time of the model's execution. And if you want to improve the readability of the chart a little bit, where it says statistic here and just the blue color, that's basically telling you that's what the line changes. So if you want to make it a little bit nicer, you can say instead of just this generic statistic, you could call this number of heavy parts, and we'll call this heavy parts versus time. And then when we run it, we see that we've got a nicer description of what this orange line means, what the line in the chart actually means. Okay, everyone good with that? Okay, so let's take a look at the next stat. So the next statistic says, what is the total dollar value of all the parts? Sorry, go ahead.
Before we move on, wasn't that supposed to be, because what we got was the total number of heavy parts, but the first bullet point is what the total weight of all the heavy parts is, right?
Oh yeah, you're right. Yep, you are right. So in that case, since this chart is only showing me how many tokens there are that meet that criteria, I need to enhance this a little bit by saying that we have a calculation assigned here. And what we want to know, like you said, is the total amount of weight those tokens represent. And that we can calculate the cumulative weight of all of the heavy subsetted tokens by looking at their weight label and adding that all together. So by putting that in, right, now I can come back to my chart and say, instead of looking at the subset content, now we're going to look at the calculation total. And the reason why it's calculation total is because we are interested here in knowing what is the total amount of heavy material that's in the zone right now. right? Because if you look at calculation input, that would be a running count of the amount of heavy material that's been received. And the calculation output would tell me the amount of heavy material that has been sent out of the zone. So if I'm interested in what's in the zone right now, or as the description says, what is currently on the floor, right, then that means that I need to choose the calculation total. And then in my drop down for the subset calculation combination, the only subset and calculation that I have is the heavy parts subset and the total weight calculation. And so on my statistic display, instead of number of heavy materials, maybe, or number of heavy parts, maybe we call this instead just weight of heavy parts. And so now we have a green line and a y-axis value that shows us how much material is located in the zone. And again, because of our limit of 3, we're going to see kind of a de facto limit around 120 to 150 pounds worth of material, because we're only allowed to have 3 heavy tokens in the zone. The heaviest of the heavy tokens is 50 pounds. So the maximum weight we could possibly see on this chart is 150 pounds. If we just let this run for a while, and kind of see that start to bear out, where we get up to as high as 150 or 140. We get a little bit higher than that. It's hard to do because the chances that we're going to get 3 tokens there at max weight is not great. Not a huge chance of that happening. But again, you can see where that ceiling is starting to be enforced based on the limit for the weights of the tokens. So good catch. Thanks for reminding me that we needed the calculation for that part. Right. And so again, if we take a look at the zone properties, we already had the subset that defined heavy things. We just needed to add in this part that says we needed to calculate the weight of those heavy things by calculating the sum of all of the weight labels of all of the tokens in this particular subset. Okay, so for the second stat, the stat is asking us for the total dollar value of all the parts that have been through the factory. So there's a couple of things to parse there, where since it's talking about the total dollar value, that's telling us that we want the stat in terms of the dollar value. So similar to the first stat, rather than having the stat in terms of how many tokens are heavy, we want the stat in terms of what those tokens are worth in terms of their dollar amount. So that's going to lead us to making another calculated stat. And because we're talking about all the parts, that means that this is a stat that's associated with the subset that includes all of my tokens. And because we're talking about things that have been through the factory, that tells me it's a throughput-based statistic. So let's come back over to my zone properties. Now, this stat is the reason why I chose to do this constraint as a subset constraint rather than the maximum content. Because I knew, because of this statistic where we want the dollar value of all parts, that I was going to need a subset that included all parts in order to perform this calculation that says, I want to know the total dollar value of all of my parts. So I tell the calculation to look at the dollar value label on all of the tokens that meet this criteria, which is everything that comes into the zone. So this gives me access to the stat. But again, I need to create a chart that actually allows me to display that stat. So we're going to say apply there, just so I can leave the window open. And then back on my dashboard, I'm going to create another zone statistic. And this time I'm going to choose a table view for this chart. And I'm actually going to create this in the other dashboard window. Just kind of move this out of the way. I'm going to rename this chart. We're going to call this like total revenue or something like that, because what it's going to report is the dollar amount that these tokens are worth. And we need to direct the chart to the zone. So we know we're getting our stats from here. And then in my stat drop down, because it's a calculated stat, I want to look at my calculation options. And because we are interested in the dollar amount of things that have been through the factory or through the zone, that means I'm going to want the calculation output. Because I don't want to know the amount of each individual thing as they leave the zone. I want to keep a running total of everything as it leaves. And so in order to do that, I need to look at the output based stat. And then on my subset calculation drop-down menu, I need to say this is the stat associated with all of my parts and their total dollar value. Now, we have some checkboxes here. When we have the table view, we have some options of whether we want to show the min, max, or average value, this kind of a chart. But none of them, like average doesn't really make sense, maximum doesn't really make sense, min doesn't make sense, current makes sense. Because this is going to be the current value of the output. And just to make the text a little bit bigger, make that 20, reset. And for some reason, it's not undrawing my min, max, and average. So let's just let it run, see if it figures it out. Reset. Might have to reload the UI. Interesting. For some reason, it is not hiding the bars that it's supposed to hide.
I was doing that a little bit too. I couldn't replicate it.
That is interesting. Huh. Strange. The UI for that looks a little bit buggy. I'm not sure what's going on there. Another one I'm going to have to report. In any event, let's just pay attention to the current value. So when you hit reset and run here, and I'm going to slow it down. So when we see the first token actually leave the zone, right? Current right now says 0 because nothing has left. And then when we get our first token that leaves the zone, we can see that our current value has increased by 185. So one token left the zone. It was worth $185.90. The next token to leave the zone, and there we had 2 that left. And so after 3 tokens left, we had a value of $1,300, $1,370 and 35 cents. And so as we let this run on, then we'll just see that this current value is always going up in accordance with the dollar amount that that token represents. Okay, so again, the pieces that we needed for that, we needed a subset that included all of our tokens. And then we needed a calculation that calculated the total dollar amount. And then our chart looks at that stat by looking at the calculation output of the all parts total dollar value combination.
Hey, Reen, can you explain the calculation output versus calculation total again?
Sure. So the calculation total is asking for the calculated value that is present in the zone right now, right? That's why our chart for the heavy parts versus time is showing us this kind of a chart, because something enters and that increases our heavy content, something leaves and that decreases our heavy content. And so this is a snapshot, like at any given time, like if you were to choose like this time at 8:30 in the morning, right, there were this many tokens, or rather this much material represented by some number of tokens of heavy material in the zone, right? And so the tokens that we had in there accounted for a little over 120 pounds worth of material, right? But that's like a snapshot of like what's in there right this second. So that's why it's a total, because we're talking about the total amount that's there right now. And the output is looking at the amount that has actually left the zone, only the amount that's left the zone. So we're not taking into account the amount that entered or the amount that is present. We're just looking at the amount that has actually left the zone. So it's like a throughput-based statistic versus a content-based statistic.
Thank you.
Yep. All right, and so for the third stat, this one's a little bit simpler, where we want to know how long on average types 1 and 2 wait to be processed. So because we're talking about the status of types 1 and 2, that tells us that we are dealing with a subset, because we already have a subset that gathers these into a category for our limit of 5 up here, where it says that we only have 5 things that are type 1 or 2. And so we're going to use that same subset so we can know how long they wait to be processed. And because we're talking about things that are waiting to be processed, that means that we're interested in a stat that is happening not in the zone, but in the request queue for the zone. So this is going to be a request-based statistic. So I'm going to again start with my zone stats chart. And I'm going to get my stats from my zone. And the stat that I want is a subset-based stat, because we're only interested in what's going on with types 1 and 2. But because these are tokens in the request queue that we're interested in, that means that we need to look at these subset request-based stats. Now, subset request content means we want to know how many things are in the request queue. With subset request input, we want to know how many things have come into the request queue. Subset request output, how many things have left the request queue. But subset request stay time tells us how long they are in the request queue. And that's really what we're looking for here, because the model is asking us for how long do things wait. So if we're talking about a duration of time, that means we're talking about a stay time based stat. So we want subset request stay time, and we want this to be for our combined category of types 1 and 2. And if you want, you could uncheck everything except the average. And for some reason, again, it's not hiding those other options. And I'll just rename the chart. We'll call this T1 and 2 waiting time. So how about we spell waiting correctly? There we go. Oh, and there it is, waiting time there. I wonder if I have to change the, is that enough? Yep, that's enough. So if you change the name, apparently, interesting. And that fixed my problem. Okay. So if we hit reset and run now, we'll see that the average time spent waiting in the request queue changes as we have more things that are red and green waiting in the request queue. So with this arrival rate, we're probably going to see that the average waiting time is always going up, just because our arrival rate is so fast that our queue is constantly growing. And we've basically hit a point here where the queue is almost unrecoverable, where we won't ever be able to get down below like 30 on the request queue. In fact, I bet if we let this run forever, we would see that that request queue just grows forever. It never really decreases. So our average is always going up. Okay, any questions there at all so far? Okay, so for the last stat, it wants to know what is the total value. So again, we're talking about a value-based stat instead of a number of tokens-based stat. So that should tell us, again, that we need a calculation. But now we're describing a category of tokens that we haven't seen before, this idea of expensive parts. And we have their criteria here that says that expensive things have to be worth more than $800. So that means that we need a new subset with a new calculation. And because we're talking about how long, or rather not how long, we're interested in the value of things that are waiting to be processed, that again tells us that this is a request-based statistic. We're interested in the value of expensive things in the request queue. So let's start by going back to our zone properties, where we will need to add a new subset. And this subset name will be expensive parts. Our selection criteria will be where the dollar value is greater than 800. And then our calculation is to say that we want to calculate the dollar value of those parts. Okay, so again, the subset and the calculation just give me the pieces that I need to report on the stat. And then to actually show the stat, I need a chart. So now we'll come back over to the dashboard and we will grab a zone statistics chart. Again, I'll do this one as a line chart. And this chart is gathering stats from our zone. And in this case, the stat that we want is a calculation request total, because we want to know how much expensive material there is in the request queue right now. So again, it's not how much expensive, not the value of the expensive things that have come into the request queue or the value of things that have left the request queue. We want to know the value in the request queue at any given time. So that's going to be our calculation request total. And then again, I have to choose my subset calculation option where I say that I want my expensive parts and their total dollar value to be displayed. And we'll call this chart expensive waiting worth or something like that, or worth of expensive waiting parts, worth of expensive waiting parts. And if you want, you could call that stat, you could call it dollars. And so now when it runs, we got a lot of zeros there until we had our first expensive part be in the request queue. And as expensive parts come into the request queue and leave the request queue, we're seeing that value update over time. Because again, this is giving us a history of how the expensive value of those expensive parts changes as the model progresses. So I guess you could say it takes a few steps to get some of these charts set up, because you need to establish kind of the infrastructure of where you have the subset definition, so you know what tokens you're gathering stats about. You need to think about like how the stats are being reported. Are they being reported in terms of how many tokens there are, or how long they do something, or how much those tokens are worth? So that tells us things like, do we need calculations? And then knowing how to interpret, kind of what we're looking for into one of the 4 different kinds of stats, right? A throughput stat, a stay time stat, a content stat, like input, output, content, stay time. Pretty much everything falls into one of those 4 categories. And so it's a matter of figuring out, okay, now, is this a stat where we're concerned about how long something takes? That's a stay time. If we're concerned about how many things entered, that's a throughput, that's an input stat. If we're concerned about how many things leave, that's an output stat. If we're concerned about how many things are present somewhere, that's a content stat, right? And so figuring out how to translate kind of the way you think about these stats in the real world into the stats that FlexSim knows how to display, like throughput, content, and stay time. And then adding additional detail like things that have to do with subset definitions, partition definitions, and calculations. All right, any questions at all? All right, well, let's take our afternoon 15-minute break. And when we come back, we are going to begin a discussion about what I consider to be actually, before we get into that, I guess before we go to the break, there's one other thing I want to show you to kind of help give some context to why zones might be useful, and also how you might use them in conjunction with a 3D environment. Now, this is a label, or excuse me, not a label. This is a model that you guys have access to. This is in the download set of material. This is found in the examples and walkthrough section called the example conveyor zone restrictions. And the thing that I like about this model is that this actually represents a real problem that I helped a customer solve a few years ago. And I liked it so much, I put it into the training as an example. So we're going to open up this example zone restrictions and conveyors model. And basically, what this customer needed to be able to do was we needed to be able to limit flow items on a certain section of conveyor based on a custom set of criteria. Now, because this was me helping out with tech support, this wasn't a consulting problem. I didn't have an NDA with this guy. And so there's very little about what he could tell me in terms of like what the system really looked like. So this is an extrapolation of how I interpreted what he was telling me about what his system was like. So kind of imagine that we had these different conveyor lines that came down and they intersected at this shared point of conveyor that I represented as this orange conveyor. And the idea is that the flow items that were coming down these varying lines needed to have like some traffic control about how many flow items were allowed to be on this orange section of conveyor. And so my first impulse was like, well, this just sounds like a restricted area. But the problem with the restricted area that we talked about earlier is that the restricted area only really knows how to restrict based on a number of flow items. Like you say that there's a maximum content of like one token or two, or not tokens, flow items, one or two flow items or something like that. They're allowed to be in this restricted area. And it really didn't do a good job working with like variable values, like being able to say, well, sometimes it's one, sometimes it's two. So how do we manage all of that? Well, so I asked the customer, so what is really going on in the real world? What is the real life restriction? And he said, well, I can't really tell you that because no NDA. So what he said, though, was that in the abstract is it's based on attributes of the flow items that want to go onto the orange piece of conveyor. So I was like, okay, well, can we pretend that it's a weight limit? Like maybe we can pretend that it's a weight limit on the orange conveyor that that needs to be obeyed. And he said, yeah, that's reasonable enough. It's not exactly that, but it's close enough to that in terms of the idea that you could use that as a jumping off point, if that helps me understand it. And that did actually help me understand it. So what I wanted to do then was to say, okay, flow items can come down the red, green, and blue conveyors, but then when they reach the orange conveyor, there is a weight limit of how many flow items are allowed to be here. So I'm going to set an arbitrary weight limit, because again, he couldn't tell me what it really was, of 50 pounds. Let's say that all of the flow items are assigned a random weight. And so I did that on the source object using the onCreation trigger, where I said that we have a label where the weight is assigned according to the uniform distribution from 15 to 50. And so all of these source objects are doing that. And I gave them labels for their type and color just so I could identify them. So red flow items are going to come on the red conveyor, green flow items on the green conveyor. And just all of these items are going to have this random weight assigned to it. Now, this was pretty early on in the days of process flow, back when really only the developers have a lot of familiarity with it. And so I was kind of thinking, well, geez, this would be a lot of code to have to write to manage this. I wonder if there's something new in this like cool process flow library that just came out that would let me do this, but maybe a little bit more easily. And so I was learning about how to use the zone, and I was like, gosh, this sounds like something the zone could do. But there's a problem that the zone deals with tokens and the conveyors deal with flow items. So how do I make the zone control what flow items are doing? Well, event listening played in heavily into this. So the first thing that I needed to know was, how do I know when a flow item wants to go to the orange conveyor? So I set up a couple of decision points here that were my signal points that said a flow item would like to go to the orange conveyor now, please. And so I created an event triggered source that listened to a group of decision points that I called my entry points. And I listened for the on arrival event, and I assigned them a label that referred to the item that actually arrived to the decision point. And then I thought, well, those tokens that I create, they need to know about the weight of the flow items that they represent, right? I can assign the item label using the event triggered source, but I would need an assign labels activity that says, I want to get the weight information from the item that is assigned to the token. So notice this kind of a neat expression here where we're saying token.item.weight, which allows me to first reference my token and then reference the item that is assigned to that token, and then reference the weight label that is assigned to that item. And this allows me to assign this data to my token and store that in a label called weight. So that was kind of like one of the first big breakthroughs for me. Is like, oh, I can kind of like synchronize the data between the flow items and the tokens by getting label values from one thing and putting it on another. So let's just see what that looks like when we see our first, and I'll just attach the rest of this here. So when you see the tokens arrive to the decision point, so you can see here we've got a token that says, well, I represent this flow item that's on the restricted lane called box. My weight is 49.38. My type is 2, so that's the green box. And then this red box says, I represent the box on restricted lane 3, which is this lane. And my weight is 47.51 and my type is 1, so that's my red box. So the box actually does have that data on it. You can see that it has its type and its weight. Green box also has its type and its weight. And I just copied that information from the flow item and assigned it to the token using this assign labels activity. Okay, so that was kind of like the first hurdle that I needed. I needed a way for my tokens to be a proxy for my flow items in process flow, because I can't put I can't put flow items into a zone, but I can put tokens into a zone and let the zone work with those work with that token data. Now, the next trick that I needed to be able to pull was to say, all right, well, we need to tell the flow items to stop and wait for available space to become available before they're allowed to move again. So what I did first was to say that, well, if you reach your decision point, we are going to tell your flow items to stop. So this is that custom code activity that we mentioned briefly yesterday to do things like state changes on objects. There's an option built into the custom code activity that says that you can control a conveyor by telling items to stop and resume on the conveyor. So I just chose this option and said, all right, we're going to tell the item that's assigned to the token that it needs to stop when it reaches the decision point. So we create the token, we synchronize the values between the flow item and the token, and then I just tell them to stop. So if you see what that looks like, that means that as flow items come down to that point on the conveyor, I just tell them all to stop. Now I tell them to stop because then I want the zone to decide whether or not it's okay to restart the flow items. So at this point, we allow the tokens to enter the zone. And on the zone, I have a subset that says to include all tokens and calculate their weight. And then I have a subset constraint that says that the total weight cannot exceed 50. Now, this is where things get a little bit interesting, because if the tokens tell their flow items to stop, the tokens don't stop, they keep going to the next activity. Right? And so if the tokens reach this point, they say, okay, tell my flow item to stop. And then they try to enter the zone. And if the zone allows them to enter, the token goes to the next activity, which is another custom code that says, now we're going to tell our item on the conveyor to restart. So there's a stop and a resume that happens in the same moment in time. There's no delays between these if the zone is ready to receive. So like what you see happen is that if a token is allowed to enter, it just gets to flow right onto the orange conveyor, and the other flow items have to stop and wait for a token to leave this restricted part of the conveyor system. And I established the exit point from this restricted conveyor by saying that we're listening to a set of exit points. And so these are decision points again, where we listen for the on arrival event of these exit points. And if a flow item hits one of those 2 points, they leave the zone, which opens up more space for the next flow item. Now, because of the weights of these flow items, usually that means we're only going to have one flow item in the orange conveyor at a time. But every once in a while, you might see 2 flow items, like right there, where 2 tokens are now waiting to exit the conveyor, or waiting for their flow items to exit the conveyor. And then when that happens, they go to the exit zone, which automatically updates the calculated stat of the zone and allows the next flow item to enter. So again, it doesn't matter which of the exit points they go to. As soon as additional space is freed up, then the next token is allowed to enter in. And so with this dashboard, I can see that the current orange conveyor weight right now is 47.74. And if we click on that green box, we'll see that its weight is 47.74. And if we get to a point where we have 2 flow items on the conveyor, happens fairly early on, so I'm just gonna get to that point. So right here, the total weight on the conveyor is 48.72, and the individual weights of these flow items, the red and the blue box, are 19.69 and 29.03. So together, these 2 boxes keep us below our limit of 50. So they're both allowed to enter into the orange conveyor because their tokens enter the zone. They tell their flow items to restart, and then the tokens just wait for the flow items to exit. And when those flow items exit, that causes the tokens to be released from the event listener and therefore be released out of the zone, thereby freeing up additional space. So I thought this was pretty cool. It was kind of a big moment, for me, because I was like, oh, I'm gonna have to write some code to keep track of the weights of all these flow items, and I have to figure out what event is going to be the incrementing event, what event's going to be the decrementing event. How am I going to establish the limit and tell those flow items to stop and then resume and all that kind of fun stuff. And instead, what I decided to do was use the zones capability to allow the tokens to indirectly control the flow of their flow items. The flow items are still behaving on the conveyor system the way they always would, but the tokens are just supplementing that with a little bit of process flow to say, hey, there's only so much room, and so we're going to tell you guys to stop, and when something leaves, we'll tell you to resume if you have space available, and that will just naturally handle the flow of traffic on the conveyor. So again, an example of process flow doing something that process flow was good at doing, and the objects doing something that the objects were good at doing. The conveyor objects are really good at conveying flow items, right? And the zone is really good at calculating restrictions based on label values. So I put those together to create this. And it worked pretty well for the customer. He was able to take this and extrapolate it to his model, and it made his model a lot simpler than it was going to be. So again, just because the zone is something that lives in process flow doesn't mean that it can't affect your 3D environment. Okay, so now we'll take our 15-minute break. Sorry about that. Okay, so like I said before the break, we're going to begin our discussion about what I consider the most important, powerful feature of the software. So a lot of what we've been talking about so far has kind of been leading us to this in the discussion of lists. So the first thing that we need to kind of get out of the way is a definition of what we mean by a list. So one of the big things that you need to remember about the list is that it is at its core a mechanism for controlling and coordinating model events. And by its very nature, it is very dynamic, which means that there is constantly during the model's runtime things that are interacting with and changing the composition of the list. One of the other big things that sets the list apart from a lot of the other stuff that we've seen so far is that it requires at least 2 sets of participants. So the very nature of the list job is to coordinate things that are happening across different areas of your model. And that means that there needs to be at least 2 things that we are coordinating with. And so there are going to be some things that are interacting with the list in one way, some things that are interacting with the list in another way. And the list is a medium, essentially, for these things to be able to work together or coordinate their events in some way. Now, this is all a little bit abstract. So the best way to kind of think about how the list works is to kind of talk about it in the context of something that we've all pretty much had experience with, we can all kind of relate to, that is a pretty good demonstration of the type of list behavior that we're talking about with the FlexSim list. So we're going to talk about it within the context of a restaurant, because this is something that we've all kind of seen a version of, where you go to a restaurant and there are tables essentially that want customers and customers that want tables. And so that's your two sets of participants. On the one hand, you have customers that are needing tables, and on the other hand, you have tables that are needing customers. And so this mechanism is essentially what the restaurant uses to be able to match you up with a table that meets a certain set of criteria, right? And so the events that are being coordinated here are the availability of tables and the desires of customers to have a meal. Now, this is different from just a simple queue, right? Now, when you go to the restaurant, say you go to a restaurant and there are a lot of people waiting, and you show up and they say, okay, and you say, okay, well, what's the waiting time for a party of 2? And they might say something like, well, right now it's about 15 to 20 minutes. And you say, okay, put me on the list, right? And what they've done then is they put you onto a list where they can say, okay, these are the customers that we have waiting. And over here on the other side, these are the tables that we have available or don't have available that we're waiting to become available, right? Now, like I said, too, this is different than just a simple queue. It's not just that you get in line and you get the next available table, right? What kinds of factors influence how long you wait on this restaurant's list? Is it just first in, first out? Is it a simple queue? What do you think?
The size of your party.
Yeah, it's going to be the big one, right? Because chances are, if you are a party of 2, you're not going to have to wait as long as that big party of 6, right? It is likely that the restaurant can accommodate a party of 2 more quickly than they can accommodate a larger party. So that is also an important feature of the list, that the time spent waiting on the list is not necessarily first in, first out, but it is rather set based on criteria. There is some criteria that needs to be met, because on the one hand, you have tables, right? And they have attributes like how many people they can sit. And the people that are on the list also have attributes like about how many people they have with them. And so the list is the mechanism that we use to allow us to match up the right customers with the right tables. And so this is also speaking to the dynamic nature of the list, where there is constantly an influx of customers that are being added and removed from the list, and also customers that are getting, and also tables that are receiving and releasing customers, right? So like when a table becomes available, you scan the list and you try to find the next best fit for that table. You take that group of people off the list and you bring them to the table, which means the table is no longer searching for a group. And so when they find a match for you, when you get taken to a table, they take your name off the list because you are no longer looking for a table, right? And so this is what I mean by the dynamic nature of the list, where there are customers that are being added to the list, and they're only on the list for as long as they're looking for a table. And when they find a table, they're removed from the list. And tables are only looking for customers as long as they don't already have customers. And then they no longer interact with the list once they find their customers. Does that make sense?
Yeah.
Okay, so like I said, this is the core idea behind the list, where there are one set of participants on the one hand, they have certain criteria. Another set of participants on the other hand, they have a set of criteria. And the list provides a mechanism where those two participants can be matched with each other in some way in order to cause something to happen. Right now, in the restaurant example, the reason why they match customers and tables using the list is because they want to get the best fit for the customer to get the best fit for the table, right? And in FlexSim models, you might use the list for a lot of different things, where you maybe want to allow order pickers to be able to know what parts they need to be able to go pick from a series of racks. And so you might give them an order list or an order sheet that says we need XYZ products. So look at the list, find those products, and then go and take them off the shelves and ship them to a customer. Or you might have a work order that says that we need to build a certain component based on a set of ingredients or reagents that says, okay, this is your build order. Now go find the necessary components. And so look at the list to see if they're available and then bring them to like maybe an assembly station and put them together in some way. So the list gets used for a lot of these different kinds of things. It's just a mechanism that says, here is a thing that is looking for some other thing. And the list provides the searching mechanism for those things to be found and matched together. Okay. Now, when we work with the list in FlexSim, there's a little bit of vocabulary that I want you to be familiar with. And first is this notion of pushing and pulling. So we say that a push happens with a list when something is like some model object is placed on the list, making it available for a pull later on in the model. So in the restaurant example, we would say that customers are pushed onto the list in order to make them available to be sat at particular tables. And so the pull is what allows us to scan the list and find the right thing that is on the list in order to cause something else to take place. And we say that the act of pushing creates what's called an entry on the list. And so an entry on the list is made up of some particular data points. We have a value, and then we also have a set of fields. So the value on the list is a reference to the entity in the model that is placed on the list. So to kind of get a feel for this, think about the restaurant again. When you go to the restaurant and they want to put you on the list, what are they really putting on the list? They're not really putting you on the list, are they? If you want to be like really kind of pedantic about this, they're not really putting you on the list. They're actually putting a way to find you on the list. They're putting a way to refer to you on the list. Maybe it's a phone number, maybe it's an email address, maybe it's just your last name that they write down on a clipboard and they're going to call it out like over the PA system. But it is a way for them to find you. But it isn't truly you because you are still a person who is able to like walk around and do things. You are not physically located on the list, but a reference, a way for the restaurant to find you is now on the list. And so that's what we term as the value. It is a reference to the thing that is pushed to the list. So like if I walk in and say, hey, I'm Blackett for a party of 2, they don't like grab me and put me on the list. They say, okay, Blackett, party of 2, we'll call you when you're ready. Okay, and so that reference to me is what we term the value. Now, when they took down my name and they also took down the number of people in my party, that constitutes a field. So a field is another part of the entry that is a searchable set of criteria that allows the restaurant to figure out which group from the list they should pull. So if they're saying, okay, well, we just had a table for 4 become available, so let's search the list for someone who is a party of 4 or less, but we're prioritizing we're prioritizing parties of 4. Right? So if you have like 2 people on the list, one's a party of 4, one's a party of 3, the party of 3 has been waiting longer, you're probably going to pull the party of 4 because that doesn't waste a seat at the table. Right? You say, well, we're going to prioritize this group because they have 4 people and this other group has maybe 2 people or 3 people, and we don't want to burn a table for 2 or a table for 4 on just like a group of 2 or 3. And so the field data that you include as part of the entry is the set of criteria that you use to determine how do we choose the right entry on the list for this particular pull when we pull from the list. And there could be a lot of things that you use as searchable criteria, right? Party size in the restaurant, that's one. maybe whether or not people prefer to sit inside or outside, maybe that's another one. If you need a table that's handicap accessible, maybe that's another one. And in like actual modeling scenarios, maybe you're saying, well, we're looking for parts that have skew A and skew B and skew C, and we're going to make sure that we search the list for things that meet that particular criteria. So pushing and pulling are how we interact with the list. So on the one hand, you have one entity that gets pushed onto the list, and that creates an entry with a value and a set of fields. And on the other side of the list equation, we have something that is pulling. So when we say that we are pulling from a list, that means that some other entity in the model is searching the list for an entry that meets that puller's criteria. And we call that act of searching a query. So a puller has the ability to query the list in order to find the best matching entry on the list that the puller is looking for. So in the case of the restaurant again, you might say that the tables in the restaurant are pullers, and they are searching the list of customers in order to find the right customer that meets their set of criteria. Like some tables are pulling customers of size 2, some tables are pulling customers of size 4, some tables are pulling customers that want to sit outside, things of that nature, right? And so because, again, of the dynamic nature of the list interaction, a pull results in the removal of that entry from the list. Because that means that if I pulled something off the list, then that's the thing that I want to get, and we remove it from the list because we don't want it to be available for any other pullers to potentially try to take as well. Because again, like in the case of the restaurant, the reason why we pull customers off the list is to find them a table. So when the pull happens, we say, hey, we found a good match for this table, take them off the list, and then cause them to go to the table and have dinner, right? So they can continue on with their flow of events. So the act of pulling just means that we've searched the list, we found something, and we removed that entry from the list. If, however, a puller searches the list and doesn't find an entry based on the criteria that they use to pull, then we say it becomes a backorder. And a backorder on the list is just a puller that didn't find something to pull, which means that they are waiting for a new push, a new thing to get pushed, that they can say, hey, does that new thing meet my criteria? Because I searched the list before and I didn't find something. So is this new thing a match for me? And if it is, then the puller gets to take it. But if it's not, then it remains a backorder. So again, think about the restaurant where maybe you just had a table for 8 become available. You don't have any customers that are party of size 8. And so that table remains empty because it didn't find a set of customers that meet its criteria. All right, now that we've kind of established the ground rules of using the list, let's actually take a look at an example of using a list to do something fairly simple, but it's a good visual example of the list behavior, where we will use what's called a global list as a means to manage flow item flow in place of port connections. Now, this is going to be a really simple example. And so rather than taking this as an example of something that you may actually end up doing in a model someday, it's more a demonstration of the concept of a list in kind of a very visual, very simple kind of a way. So we don't have to construct like a really complex model where a list is really helpful. We're just going to do this with something simple. And so in my example model that I'm going to build, again, just default units. And I'm going to create some objects. I'm going to have a source, a queue, a couple of processors, and a sink. And I'm just going to connect them together in the usual way. And now, if I run the model right now, flow items will naturally flow to the first available processor, because that's the flow definition that the queue is using right now. It says we're going to send these flow items to a port. So we're going to evaluate our ports, and we're going to decide what processors are available. Now, one of the many things that a list can do for us is that it will give us a way to gain greater control over how flow item flow is going to take place. And so rather than using the port connection logic that's just inherent with the object connections, we're going to use a different set of flow tools that have to do with using lists. And that's going to be our basis for demonstrating the list behavior and how to set up a list and use a list in FlexSim. So I'm going to reset my model. And the first thing I'm going to do is go to my toolbox. And in the toolbox, under the green plus sign, there is the option to add a global list. Now, a global list is basically a list that can be used globally in your model, like the name suggests. So that means that it's accessible from process flow, it's accessible from the object environment. And in order to differentiate from these different lists, from different ways lists can be used, we created some different classes of global lists. In each case of these global lists, the assumption is that a certain kind of modeling object is going to be the entry on the list. Like, for example, a fixed resource list assumes that fixed resource objects like processors or queues will become the entries on the list. An item list assumes that flow items are going to be pushed onto the list. And with task sequence and task executor lists, also, they assume those kinds of things are going to be pushed onto the list. The general list is kind of a blank slate list. It doesn't assume anything about what's going to get pushed, but it's provided as a template, a starting point, if one of these other lists doesn't quite fit in with what you want to do. So for this example, we're going to create an item list. Now, that means that at some point in the model, we need to cause flow items to be added to this list. Now, again, think about this in terms of the restaurant. When does the restaurant know that customers want tables? Do they just wake up one morning and they realize we're going to get these customers coming tonight?
No, when the customers show up.
Yeah, when the customer shows up, right? It's very event driven, right? People actually have to walk through the door and request a table. So that's also the case in how we use the list in FlexSim, where we need an event that says at this point, this thing gets pushed onto the list. And so we need to find an event in the model that says, this is the event where things are pushed. Okay, so creating the list just sets up the list as being available to be pushed to. And you can see here on the list properties, there are fields that are predetermined for the entries that are going to be pushed. Like, for example, we have a field that would tell us the type of the flow item based on a type label. We have a field for the age, so we know how long things have been on the list. We have distance, so that we know potentially how far they are away from the puller, and also a queue size, which tells us how many things are in the same location as the value. Remember the value, the thing that was actually pushed to the list. So this creates the list and makes it available to be pushed to. So again, I need an event that says at some point we're going to push things to this list. So I'm going to say okay to this. And on my queue, rather than saying that my send to port says that we're going to use the first available of my port connections, I'm going to go to the drop-down menu and say that we will be using a list here instead. And I'm going to say that this event, the send to port event of this queue, is my push event. This is the event where items will be pushed to that item list. So if I choose this option, it gives me a little drop-down menu. And it says that the item list 1, is the list that we're going to push to. Now, notice that the name here is the same name as what's in my toolbox. And it just knows that because it sees that I have that item list and assumes that that's the one that I want to use. Now, if I had multiple global lists and this wasn't the one I wanted to use, go to your drop-down menu and you would choose one of the other lists that you see in this menu. If you don't have a list yet, you can also use this option to create a list at this point. Then when you click off of that, it says that send to port says push to item list. Now, this means that we are bypassing the port connection logic. And rather than using port connections to determine where flow items go, we're using a list now. So if I were to hit reset and run, my flow items are going to come into the queue and they're not going to go anywhere. Because now, because I said that I want to push to an item list, those flow items are ignoring the port connections. Those port connections are now inactive, and we are pushing these things to a list instead. The assumption being at some later point in the model, we will cause these flow items to be pulled from the list, and the act of pulling them from the list will cause the flow items to go to some pulling object. And in fact, we can see this. If we come back over the toolbox and right click on the item list, I can say view entries, and I'll see a table view of my entries on the list. And so I have my value that references an individual flow item that's in the queue. The type field is blank because they don't have a type label assigned to them, but I can see the age. As they spend more time on the list, the age is always going up. Their distance right now is unknown because we don't have a puller designated for them, so they don't know how far away they are from a puller because there is no puller. And we also have the queue size, which tells us how many things are in the same location as the value. And so since they're all in the same place, the queue size is all the same. Okay. Now, since we're using a list and we're saying that at this event, things are getting pushed onto the list, if I want these flow items to be able to leave the queue, I need to establish some other object as a puller from this list, because I want to be able to search this list and find a box and cause it to be sent to some other object. So I need to now establish my other set of participants with this list. The flow items are my first set of participants, but now I need to establish who my pullers are going to be. And in this example, I'm going to say that my two processors are going to act as my pullers. So processor 1 is going to be able to search the list and be able to find flow items, and processor 2 is going to be able to search the list and be able to find flow items. So we establish these objects as pullers by going to their properties, and under the input section of their properties, you'll notice that there is a checkbox that says pull. And so this allows the processor now to be operating as a puller. Now, if you check that box, that activates two additional object properties. We have the pull strategy and the pull requirement. Now, pull strategy and pull requirement have been around for a long time, even before we had lists. And the way we used to handle pull operations on fixed resources in the past was to allow them to search through their input ports in order to find flow items that they may want to pull. It was a decent little system. It was a little bit hard to work with, and it was, I don't know, I felt like it was hard for new users to kind of really figure out how to use very well. The barrier to entry was pretty high. But similar to how we said on the queue that the send to port is actually being bypassed, and now we're using a list instead, we can do the same thing with the processors on their pull strategy by saying, instead of pulling from an input port, which is what the default says, we are going to say that we are going to use a list here instead. And in this case, we are going to say that this is the pulling event where processors are now allowed to pull from the item list. So we're going to say pull from item list here. And you'll notice that gives me two input fields where it says this is the list that we're going to pull from, which is our item list in the toolbox. And we also have a field for inputting a query so that we can indicate what things this processor wants to pull from the list. Now, for now, we're going to leave the query field blank. A blank query field means that the processor can take anything off the list. And its default search on the list is going to be to take whatever's been on the list the longest so far. So a blank query means pull anything, whatever's been waiting the longest, doesn't matter. We're not doing any kind of particular search on the list quite yet. Now, I do want to point one thing out too, is that if your pull strategy says that we are pulling from a list, ignore the pull requirement. The pull requirement does absolutely nothing if your pull strategy says to pull from a list. The only time that the pull requirement is in play is if your pull strategy involves port connections, like any port by case, or something like that. But if our pull strategy involves a list, then you might as well just pretend that the pull requirement doesn't exist, because it's not going to influence how the processor pulls. Okay, so I'm going to set up both processors to do this. So processor 1 is ready, and then processor 2 also, I'll go to input, activate the pull strategy, and say that we are going to pull from our item list with a blank query. Okay, now before I run the model, I'm going to come back to my item list in the toolbox and say right click, and I want to view my back orders. So if I view my back orders, I'll just dock the window here. The idea, remember, behind a back order, like we mentioned, is that a back order is a puller that didn't successfully find anything to pull. So right now at time 0 of the model, both my back order queue is empty and my list is empty. But if I come up to the toolbar and say reset, notice now that processor 1 and 2 have been added to the back order queue. Because the event that I chose to establish them as pullers is the pull strategy, the pull strategy event is actually going to fire as soon as the model clock starts to run. So this means that the processors are already in the back order queue waiting to pull something off of the list. And so they're back orders because they've essentially looked at the list and they said, well, there's nothing there yet. So now we are back orders waiting to pull something. Now, I also want you to notice the order in which these processors are added to the back order queue. Processor 1 was added to the back order queue first because I created processor 1 first, and processor 2 is second in the back order queue because it was created second. Okay, so by default, the back order, or rather the processors, are added to the back order queue in the order in which they were created. Once the model starts running, we're going to see that they get removed from the back order queue and added back into the back order queue as the model executes. And that's going to influence which back order gets to pull first. So if we begin to run, our processors are the back orders, and we're going to wait until we get our first flow item to be pulled, and then I'm going to pause the model. So right there, processor 1 pulled first. That flow item came into the queue, it was pushed, there were back orders already there waiting for it, and the first or oldest back order got to pull from the list first, and so that means that processor 1 gets the first box. Now notice that that processor 1 is no longer a back order because it found something to pull, and so it takes itself off the back order queue. And it doesn't get added back until it gets done processing. So now processor 1 has been added second to the back order queue. So that means that processor 2 has now been waiting longer. And so the next flow item to arrive gets pulled by the next oldest back order, which in this case is processor 2, which moves processor 1 back up to the highest point in the back order queue. So the next flow item is pulled by processor 1. And we see that those processors will be added and removed from the back order queue as they pull things from the list. And we'll only see entries on the list if we have more flow items than what the processors can pull. So if we have more flow items than we have availability on the processors, that's when we see entries accumulating on the list, like right now. Okay, so now remember, all things being equal, processor 1 and processor 2 are competing for the flow items, and because their queries are blank, they want all the same kinds of flow items. And so whether processor 1 pulls something or processor 2 pulls something depends on who got into the back order queue first. And the flow items are getting pulled as soon as they arrive, for the most part, because both processors will take anything. And so as soon as something arrives, if you have an available processor, they're getting pulled immediately. And the act of pulling in this case is actually causing the flow items to be sent to the puller. So the pullers look at the list, they find something that they want to pull, the entry gets removed from the list, and then the processor says that the thing that I pulled needs to be moved to me. And that's what causes them to be moved to the processors. But that's only happening because the processors are acting as pullers during their pull strategy event, which means that the resulting action of the pull from list is going to be to cause the flow items to go to the processors, to the pullers. Okay, any questions at all? Okay, so far this is pretty simple, and we haven't seen anything like so very earth-shattering yet. That's like, well, okay, that's neat and all, but why would you want to do this? Why is this better than port connections? Well, at this stage, it's pretty much sixes which way you would want to do things. One of the nice things though about using the list is how we can use the query options on the pullers to allow the pullers to be more particular about the kinds of things they want to get from the list. So let's make things a little bit more interesting. I'm going to reset, and in my source object, I'm going to say on creation, and we will set a label and a color. And I'm just going to use all the default options. So the label will be assigned to the item, label name is type, and label value is from D uniform 1 to 3. And now let's say that processor 1 is a little bit picky. Maybe processor 1 only wants to take things whose type is equal to 1. So that means that I can come back to my pull strategy and go to the options for this property. And in the query field, I'm going to say that I want to pull things where type is equal to 1. Okay, now when I clicked on that green plus sign, this gives me a couple of options for creating a query. There are 2 different clauses that you can have as part of a query here. You can have a where query, which is a filtering mechanism, and you can have an order by query, which is a sorting mechanism. Now, in both cases, the things that you're allowed to filter or sort by are fields that are assigned to the list. So notice that when we look at this menu, it says, okay, you can filter on type, age, distance, or queue size, or you can order on type, age, distance, or queue size. So with this implementation of things, I have to have some kind of a searchable criteria that I want to use assigned to the entries. And so here, if I say where type is equal to 1, that means that I want to filter what processor 1 receives by looking at the type field and only considering things whose type field value is equal to 1. Okay, so let's see what that looks like. If I hit reset now, you'll notice in the backorder queue that we can see the query that processor 1 is using. And now when we run it, the first flow item that comes in happens to be a red box, which is type 1, which means that the processor pulls it. And the next flow item that comes in is blue, which is type 3. And now notice that there are blue and green boxes that are queuing up because processor 1 is looking at them on the list and saying, nope, you aren't the things that I want. I'm looking for things where type is equal to 1. You are where type is equal to 2 or where type is equal to 3. So I will not consider you. right? So processor 2 now is still able to accept anything, but processor 1 is ignoring anything that's green or blue because its query says, I only want things where type is equal to exactly 1. Now, that doesn't mean that the query is mutually exclusive, right? Here is a situation where processor 1 pulled a red box and processor 2 pulled a red box, right? Just because processor 1 is saying, I only accept things that are type 1, that doesn't mean that processor 2 can't take things that are type 1. It just means that processor 1 is only looking for that type. Processor 2's query still says, I can take anything. My query field is blank. I'll take anything in any order as soon as I can get it, right? So if there are enough red boxes in the queue, then processor 1 and processor 2 both might pull the same kind of item. Okay, any questions so far about the where query? Okay. So let's take a look at the other clause that we can add to our queries. And we'll go to processor 2 and do an example of what we call the order by query or the sorting query. So the order by query allows us to define a method where we will prioritize different eligible entries for the pulling. So an order by query means that if you look at the list and there are multiple entries that meet your criteria, then the order by query allows you to say, well, what order do I want to take those entries? What is the sequence of priority where I should say, well, if there are like 5 entries that are all entries I could possibly pull, how do I want to go about prioritizing them? Like, is there some value that says we should take these ahead of these ahead of these, right? And so if I say that I want to order by type, this means that I want to sort what this processor receives according to the type field. And then after that, it gives me a way to define the sort direction. So this ASC stands for ascending. So in an ascending sort means that you would sort the lower values ahead of the higher values. So type 1 would be sorted ahead of type 2, which would be sorted ahead of type 3. So in the case that you have flow items that are all type 1, 2, and 3, and they're all competing for the processor, then the order by query allows you to say, well, I could pull any of these, so I will pull the one whose type is the lowest because I'm doing in an ascending sort. Alternatively, if you exchange the ASC for a DESC, whoops, that stands for descending. So that would mean that we're now doing a descending sort where we evaluate the type field, and in the event of a tie where we could pull multiple things, we will prefer things whose type value is higher than the others. So you would start at the highest value and descend down towards the lower values. So order by doesn't exclude you from pulling anything on its own. It just says this is the order in which you will take things. You will take things from the list such that the type is sorted in a descending direction. Okay, so let's see what that looks like. If we hit reset and run, again, processor 1 is still only taking things that are type 1. So we'll see only red boxes go across processor 1. And now there's nothing on the list, so we're waiting for our next entry. Okay, now, actually, let me start this over again. I'm just going to turn up the arrival so it happens a little bit sooner, so I don't have to wait as long. So I'm going to say that we create something every 3 seconds. Okay, so there's our red box, blue box, green box. So here's a situation where we have a green box and a blue box both in the queue. And we can see them as entries on the list, right? And so the type 2 box has an older age on the list, and the type 3 box is newer. Now, processor 2 says that I am sorting what I receive by doing a descending sort on type. That means that I want the higher values first. So which flow item is going to be pulled by processor 2 next? The red one or the green one? Or the green and the blue one, sorry.
It's always going to pick the blue.
Yeah, it's going to pick the blue because blue is a higher type compared to the green and the red. And so as long as there are blue boxes in the queue, the second processor will take the blue boxes. If we don't have any blue boxes, then we will take green boxes. If there are no green boxes, then we'll take red boxes. Processor 1 is still only ever taking red boxes. But processor 2 is trying to get rid of all the blue boxes before we pull any green boxes, because that's what its query says to do. Its query here says, I want to sort what I receive by type in a descending direction. So give me blue boxes before green boxes before red boxes. Okay, so in this example, I have one processor doing a where query and the other processor is doing an order by query. But the different clauses, the different kinds of queries that you can run in a query on the list like this are not mutually exclusive either. You can combine wheres and order bys, and you could say where this, or this, where this, and order by this. Right, you can really come up with some really interesting and complex search criteria that your pullers are allowed to use when they search the list. You can get really creative with it, and the syntax that we use is based on a database language, a pretty common database language called SQL. So if you have any familiar with SQL database queries, then you've got a leg up on how to use lists. But even if you don't have like a great background in SQL, you don't really need one because the query builder options here with the plus sign will kind of help you out on the kinds of things that you can query. You just need to add the searchable criteria to the list property, so you can say these are the things I want to potentially search for, and then it's a matter of saying, okay, do I want to filter what I receive based on this field, or do I want to sort what I receive based on this field?
So,
and you can use. Sorry, go ahead.
Does it matter how you make your query statements then? Do you have to have the where or the order by clause first?
If you use the query builder, it'll do it for you, right? So like in my processor 2, I have an order by clause, right? But if I say, oh, actually, I want to also sort what I receive by type, such that I want to take things that are not equal to 1. Notice how it put the where clause first. It just filled that in for me. So let me do that again. So if you were to say, well, I've got my order by statement, and if I come in and say where now, where type, it fills in the where, because the sequence that you order these things is to do wheres and then your order bys. Where clause comes first, order by comes second. The idea being that you're going to do a filter. We're going to exclude certain things from being considered for the pull, and then you're going to sort what's left over by some kind of an order by statement. But the query builder with the plus sign will make sure that everything gets put in the right order if you're not comfortable with that. But otherwise, just remember that your where clause comes first, and then your order by clause comes after. that make sense?
Yeah, thank you.
Okay, so with the couple of minutes that we have left here, I just want to give you guys a quick little exercise that has you build a model using a global list as a way to manage flow item flow. So it's really similar to the little walkthrough example I just did, but with a little bit more going on. So we're going to say that we have a source that creates flow items every 2.5 seconds, and those flow items are sent to a random downstream queue. So we just wanted to say that the send to port of this queue, or excuse me, of this source says to send things randomly to these queues. And then when the flow items arrive, using the send to port event of those queues, we want those flow items to be pushed onto an item list. And then we have 4 processors that are going to be set up as pullers from the item list. And in the challenge section, we want to filter what the processors receive according to type. So the first processor will pull type 1, second processor type 2, third processor type 3. But the fourth processor, we want it to be able to pull things that are either type 1 or type 3. So kind of skipped over this. Upon creation, when you create those flow items, we want to assign them a type label and a color using duniform 1,3. Then we want to push them to a list, let the processors pull them from a list, and then use the query of the processors to pull things so that all type 1s are pulled here, type 2s here, type 3s here, and then your fourth processor, type 1 or type 3, can be pulled. Sound good?
Yep.
Okay. So kind of like what we did last time when we ended the day on a modeling exercise. Work on it until about 4 o'clock. If you're done, great. If you're not done, don't worry about it. We'll have some time to finish it up tomorrow. And just when you're satisfied, you can go ahead and drop, and we'll just see you tomorrow. Okay, good luck.